Right now, as you listen to these words, you're moving at about 1,000 miles per hour. Not through your own effort, not by any choice you made, but because the planet beneath you is spinning, rotating, turning on its axis at a speed that would seem impossible if you could feel it. But you can't. None of us can. The motion is so constant, so smooth, so utterly reliable that it's invisible to our senses. Until you imagine it stopping. Tonight we're going to explore that impossibility together. Not the gradual slowing that's actually happening. Earth's rotation does slow by tiny amounts each year, but a sudden, complete stop. What would happen if Earth's spin simply ceased? If the planet that's been turning for 4.5 billion years suddenly became still? Hello, and welcome to the Sleepy Astronomer. If you're joining me for the first time, welcome to this gentle exploration of cosmic what-ifs. And if you've travelled with me before through vanishing suns and binary stars, it's wonderful to have you back for another thought experiment. Whether you're settling into bed, finding a comfortable spot, or perhaps lying somewhere feeling the stillness that isn't really stillness at all, I'm so grateful you're here to explore this question with me. If you enjoy these peaceful journeys through space and science, I'd be so grateful if you'd subscribe to join us for more cosmic explorations. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through what-if scenarios. Now let me offer you this comfort right away. Earth isn't going to stop spinning. Not suddenly, not catastrophically, not in any time frame that matters to us. This is a thought experiment, an impossible scenario we're exploring not to frighten, but to appreciate. To notice what we take completely for granted. To understand the motion we can't feel but can't live without. Because here's what makes this question so fascinating. That 1,000 mile per hour spin gives us everything, day and night, the rhythm that all life on Earth evolved to follow. Weather patterns driven by the Coriolis effect. The spreading of heat from the equator toward the poles. Even the very shape of our planet, the slight bulge at the equator, exists because we're spinning and we never think about it, never acknowledge it, never appreciate it, until we imagine it gone. Tonight, we'll explore what would happen in that impossible moment when the spin stops. The immediate chaos, yes, but then beyond that, what would Earth become? A planet with one face always toward the sun and one face forever in darkness, the scorching day side, the frozen night side, and between them the Terminator zone, that narrow band of perpetual twilight where life might somehow persist. We'll discover what it means to live in eternal day, eternal night, or that strange twilight between, how weather would change, how life would adapt whether humanity could survive, and ultimately, what this impossible scenario teaches us about the gift of motion, the spin we never notice, but that makes everything possible. So, find your most comfortable position, take a deep breath, and let yourself relax into this journey through stillness and motion, through catastrophe and adaptation, through the physics of the impossible. The question is simple. What if Earth stopped spinning? The answer? Well, the answer will take us to some unexpected places. Right now, as you're listening to this, you're moving at roughly 1,000 miles per hour. Not through choice, not through effort, but simply because you exist on the surface of a spinning planet. At the equator, that speed is about 1,040 miles per hour. If you're closer to the poles, it's a bit slower, maybe 700 miles per hour in the mid-latitudes, eventually reaching zero if you're standing exactly at the North or South Pole. But unless you're camping on the polar ice, you're moving. fast, and you can't feel a thing. This is one of the most remarkable facts about our existence, and we barely think about it. We go about our days, drink our coffee, walk our dogs, completely oblivious to the fact that we're passengers on a massive carousel that never stops. The reason we don't feel this motion is beautifully simple. Everything around us is moving at exactly the same speed. The air, the ground, the buildings, your coffee cup. Everything. There's no wind in your face because the atmosphere is spinning right along with you. It's only when something changes speed that we notice motion at all. Imagine you're in a car travelling at 60 miles per hour on a perfectly smooth highway. If you close your eyes, you might not even realise you're moving, at least until you hit a bump or take a turn. Earth is like that car, except the highway is space, and there are no bumps. We're in what physicists call constant velocity motion, and our bodies simply have no way to detect it. We only notice acceleration, deceleration, or changes in direction. Smooth, constant motion, invisible. This spin gives us something so fundamental we literally can't imagine life without it. The 24-hour day, sunrise, sunset, the rhythm of light and dark that every living thing on this planet has evolved to expect and depend on. We wake, we sleep, we structure our entire existence around this cycle. And it exists purely because Earth spins. But here's where it gets interesting. For most of human history, we didn't know Earth was spinning at all. It certainly doesn't feel like it. The ancient Greeks, brilliant as they were, mostly believed Earth sat still at the centre of everything while the heavens rotated around us. It's an understandable mistake. When you look up at the night sky, it really does look like the stars are wheeling overhead while you stand perfectly still. The first person to seriously suggest Earth might be spinning was Aristarchus of Samos, way back around 250 BCE. He proposed that Earth both rotated on its axis and revolved around the sun. It was a radical idea. So radical, in fact, that almost nobody believed him. It would take nearly 2,000 years before the idea caught on, thanks to Copernicus and Galileo. But even then, proving Earth spins was surprisingly difficult. The best proof came in 1851 when a French physicist named Léon Foucault hung a 67-metre pendulum from the dome of the Pantheon in Paris. As the pendulum swung back and forth, something remarkable happened. Its plane of swing gradually rotated over time. The pendulum wasn't changing direction. Earth was rotating beneath it. It was the first direct visible evidence that we live on a spinning world. People came from all over Paris to watch this pendulum slowly reveal a truth about our planet that we'd never been able to see before. Now, this spin does more than just give us day and night. It actually shapes the planet itself. Earth isn't a perfect sphere. It's slightly squashed at the poles and bulges at the equator. That bulge exists because of centrifugal force. As Earth spins, everything at the equator is constantly being flung outward, just a little bit, over billions of years. That constant outward force has made Earth about 43 kilometers wider at the equator than from pole to pole. It's not much in the grand scheme, less than 1% of Earth's total diameter, but it's measurable. Our planet is slightly ablate, a stretched sphere because of spin. And then there's the Coriolis effect, which is possibly one of the most important consequences of Earth's rotation that nobody really thinks about. Here's how it works. Imagine you're standing at the North Pole and you throw a ball toward the equator. From your perspective, the ball curves to the right. But here's the thing. The ball is actually travelling in a straight line. It's just that Earth is rotating beneath it, and different latitudes move at different speeds. The equator is spinning faster than you are at the pole, so by the time your ball travels south, the ground beneath it has moved. From the ground's perspective, the ball curved. This effect is responsible for the way weather systems spin. In the northern hemisphere, storms rotate counterclockwise. In the southern hemisphere, clockwise. It's why hurricanes have that distinctive spiral shape. The Coriolis effect also drives ocean currents, influences wind patterns, and even affects long-range artillery and missile trajectories, all because Earth spins. But here's something that might surprise you. Earth's rotation also generates our magnetic field. Deep inside our planet, about 3,000 kilometers down, is a core made mostly of iron and nickel. The outer part of this core is liquid, and it's in constant motion, swirling, churning, flowing in enormous convective currents, driven by heat from the solid inner core. As this liquid iron moves, it generates electrical currents, and those electrical currents create a magnetic field. This is called the geodynamo. Now, Earth's rotation doesn't create the magnetic field directly, but it does organize those currents in the core, giving the field its overall structure. The field extends far out into space, creating a protective bubble called the magnetosphere. This bubble deflects most of the solar wind, the constant stream of charged particles flowing out from the sun. Without this protection, those particles would gradually strip away our atmosphere. It's what happened to Mars, which lost its magnetic field billions of years ago and subsequently lost most of its atmosphere. Earth's spin, through this chain of effects, helps keep our air from blowing away into space. So rotation gives us day and night, weather patterns, ocean currents, the shape of our planet, and protection from the solar wind. Not bad for something we can't even feel. But here's where the physics gets really beautiful. Earth keeps spinning because of something called conservation of angular momentum. This is one of the fundamental laws of physics, and it states that a rotating object will keep rotating unless something applies a force to stop it. In space, there's no friction, no air resistance, nothing to slow Earth down. So once it started spinning, back when our planet was forming from a swirling disk of gas and dust about 4.5 billion years ago, it just kept going, and it will keep going for billions more years. Except it's actually slowing down, very, very gradually. The main culprit is the moon. Tidal forces, the same forces that create ocean tides, create friction between Earth's oceans and the ocean floor as they slosh around. This friction acts like a very, very gentle brake on Earth's rotation. We're losing about 1.7 milliseconds per century. That doesn't sound like much, and on human timescales it isn't. You will never notice Earth's day getting longer. But over geological time, it adds up. 400 million years ago, when the first forests were appearing on land and fish were just beginning to venture onto shore, a day was only about 22 hours long. Go back even further, back to when Earth was young, about 4 billion years ago, and days were only about 6 hours long. Earth was spinning so fast that a complete day-night cycle took just a quarter of the time it does now. And this process continues. In about 600 million years, if nothing else changes, a day will be 25 hours long. Eventually, in the very distant future, we're talking billions of years from now, Earth might become tidally locked to the moon, just as the moon is already tidally locked to Earth. At that point, one Earth day would equal one lunar month. About 27 current days Earth's rotation would slow until one side permanently faces the moon. But that's so far in the future it's almost meaningless to us. For now, and for millions of generations to come, Earth spins at roughly the same rate it does today. One rotation every 24 hours. One sunrise, one sunset, one complete cycle of light and darkness. The rhythm that life on Earth has danced to for billions of years. We are already spinning. We're moving through space at incredible speeds, held to the surface only by gravity, carried along by a planet that has been rotating since before there was life, before there were oceans, before there was even a solid surface to stand on, and we don't feel a thing. It's worth pausing to appreciate that. The motion we never notice, the spin that makes everything possible. Because in a moment, we're going to imagine what happens if that spin simply stops. So what if Earth's rotation just stopped? Not gradually, not over millions of years, but suddenly. One moment we're spinning at 1,000 miles per hour, and the next moment, nothing, complete stillness. Let's be clear right from the start, this cannot happen. It's physically impossible. The reason has to do with one of those fundamental laws of physics we mentioned earlier, conservation of angular momentum. A spinning object keeps spinning unless something applies force to stop it. And Earth is big. Really, really big. The amount of energy you'd need to stop it spinning is incomprehensible. You'd need to dissipate all of Earth's rotational kinetic energy, which is about 2.6 times 10 to the 29th joules. For context, that's roughly the amount of energy the Sun outputs in an entire week. There's simply nothing in our solar system that could apply that much force instantly. But we're going to imagine it anyway, because thought experiments, even impossible ones, have a way of teaching us about the world we actually live in. They help us appreciate what we have by showing us what we'd lose. And in this case, what we'd lose is, well, everything. Let's set up our scenario carefully. We're imagining an instant stop, not a gradual slowdown over years or centuries, but a sudden halt. At exactly noon on some ordinary Tuesday, Earth's rotation simply ceases. The planet stops, but everything on it, and this is the critical part, everything on it still has momentum. You're standing on the equator, moving at 1,040 miles per hour. The ground beneath your feet suddenly stops. You don't. Neither does anything else that isn't literally bolted to the bedrock. The air, the oceans, the buildings, the trees, the birds in the sky, everything continues moving eastward at whatever speed it was going before the stop. Let's start with the atmosphere, because that's the most immediate problem. The air around you is moving at 1,000 miles per hour. When the ground stops, the air keeps going instantly. You're standing in winds that make the worst hurricane in recorded history look like a gentle breeze. For reference, the strongest wind ever measured on Earth was about 250 miles per hour during a tornado. We're talking about winds 4 times that strong. Everywhere, all at once. These aren't winds that knock you over. These are winds that turn everything into projectiles. Every loose object, cars, houses, trees, anything not anchored to bedrock, becomes a missile travelling at supersonic speeds. The shockwave alone would be devastating. The friction from air moving that fast would generate enormous heat. In seconds, the surface of the planet would become a scene of total destruction. And then there are the oceans. Imagine all the water in all the oceans on Earth moving at 1,000 miles per hour. When the continents stop, the water doesn't. It keeps going, piling up, creating tsunamis that dwarf anything we've ever experienced. We're not talking about waves that are 10 meters high or even 100 meters high. We're talking about walls of water, kilometers tall, circling the entire globe, moving at highway speeds, drowning everything in their path. The initial wave would start at the ocean floor, where the water is deepest and moving fastest. It would build as it travels, gathering more water, increasing in height until it reaches the continental shelves, and then it would just keep going. Inland, across entire continents, a moving mountain of water carrying everything, ships, buildings, whales, ocean floor sediment, all of it crashing across the landscape. Now, there is a small mercy in all this chaos, though calling it a mercy feels almost absurd. The effects would be less severe near the poles. Remember, the rotational speed of Earth's surface depends on latitude. At the equator, you're moving at 1,040 miles per hour. At 45 degrees latitude, roughly the latitude of Minneapolis or Milan, you're moving at about 735 miles per hour. At 60 degrees, the latitude of Oslo or Anchorage, you're down to about 520 miles per hour. And at the poles themselves, you're not moving at all, at least not from rotation. So if you happen to be at the North or South Pole when Earth stopped spinning, you'd experience something strange. The ground would stop, but you were already basically stationary, at least rotationally. You wouldn't be flung anywhere. The air around you wouldn't suddenly become a supersonic hurricane. You'd just stand there, probably very confused, while the rest of the planet experienced apocalyptic devastation. But even at the poles, you wouldn't be safe for long, because while you might survive the initial stop, the consequences that follow would affect the entire planet. We'll get to those in a moment. Let's talk about the physics of what's happening here, because it's worth understanding why this is so destructive. When Earth stops, all that rotational kinetic energy has to go somewhere. Energy can't just disappear. That's another fundamental law of physics. So where does it go? It converts, mostly into heat and destruction. When the atmosphere hits the ground, all that kinetic energy turns into heat. When the tsunamis crash into the continents, that energy becomes heat and sound, and the kinetic energy of flying debris. When buildings shatter and trees snap and mountains erode in seconds, that's energy being transferred and transformed. The total energy involved is staggering. We mentioned earlier that Earth's rotational kinetic energy is about 2.6 times 10 to the 29th joules. All of that energy gets released in minutes. For comparison, the asteroid impact that killed the dinosaurs released about 4 times 10 to the 23rd power joules. We're talking about an event roughly 1,000,000 times more energetic than the extinction of the dinosaurs, distributed across the entire planet. Simultaneously, the surface of Earth would heat up dramatically. The friction from the atmosphere alone would be enough to ignite fires across vast swaths of the planet. The oceans would churn and boil at their surfaces. The sheer amount of kinetic energy being converted to heat would make most of the planet's surface uninhabitable within minutes. Now here's an interesting thought. What if the stop wasn't instant? What if, instead of halting in a single moment, Earth slowed down over, say, an hour or a day? Would that make things survivable? The answer is, it would help, but not as much as you might think. The problem is still the same. You have to dissipate all that energy somehow. A slower deceleration means the energy release is spread out over more time, which means less intense heating and wind at any given moment. But you're still dealing with enormous forces. If Earth took a full day to stop, you'd experience sustained hurricane-force winds that would gradually intensify as the deceleration continued. The oceans would slosh back and forth, creating waves that, while not as catastrophic as the instant stop scenario, would still cause massive coastal flooding. The longer the deceleration, the more survivable it becomes, but you'd need weeks or months to make it something humans could actually endure. And even then, the long-term consequences we're about to explore would still happen. So let's assume, for the sake of our thought experiment, that somehow, through magic or science fiction or divine intervention, the initial stop happens, the chaos settles, and some life remains, maybe deep in bunkers, or in the ocean depths, or through sheer impossible luck. Let's assume the immediate catastrophe passes. What happens next is in many ways even more interesting than the stop itself, Because now we have to think about what Earth looks like when it's not spinning, and that's where things get truly alien. The first thing to understand is how a non-spinning Earth relates to the Sun. Right now, Earth rotates once every 24 hours, while also orbiting the Sun once every 365 days. These are two separate motions. If rotation stops but the orbit continues, Earth still goes around the Sun, but it no longer spins as it does so. This means that Earth would become tidally locked to the Sun, much like the Moon is tidally locked to Earth. One face of the planet would permanently face the Sun, the other face would permanently face away. No more day-night cycle, no more sunrise or sunset. Just eternal day on one side, and eternal night on the other. Well, almost. There's a technical detail here worth mentioning. True tidal locking occurs when an object's rotational period matches its orbital period. For Earth, that would mean one side faces the Sun for the entire year-long orbit. But actually achieving tidal locking takes time, millions or billions of years of gravitational interaction. In our impossible scenario where Earth just suddenly stops spinning, we're not really creating true tidal locking. We're creating something perhaps even stranger, a planet that doesn't rotate at all relative to the stars, which means the Sun would slowly creep across the sky over the course of a year. But for our purposes, let's imagine the cleaner scenario. One hemisphere always faces the Sun, one hemisphere always faces away. It's simpler to think about, and it helps us understand the consequences. In reality, the slow rotation over a year would moderate some of the extreme effects we're about to describe, but the basic principles remain the same. So now we have a planet with one side in perpetual daylight and one side in perpetual darkness, and between them a narrow ring of twilight, the Terminator zone, where the Sun sits forever on the horizon. This is where things get interesting, because a non-rotating Earth isn't just a stopped Earth, it's a fundamentally different kind of planet, with completely different climate zones, different weather patterns, different possibilities for life. The day side, the night side, and that thin band between them would each become their own distinct worlds. And understanding what each of these zones would be like, what you could find there, what could survive there, whether humans could live there, that's what we're going to explore next. We've imagined the catastrophe. We've survived the impossible. Now, let's explore the strange new world that emerges from stillness, starting with the day side, where the Sun never sets. Imagine waking up to a sun that never moves, not rising, not setting, just hanging there in the sky at the same angle, hour after hour, day after day, forever. That's life on the day side of a stopped Earth. Well, almost forever. Remember, Earth is still orbiting the Sun, so over the course of a year the Sun would trace a small path across the sky, rising slightly in summer, dipping slightly in winter, but on any given day it would appear essentially motionless. No dramatic sunrise, no golden hour, no sunset painting the clouds, just constant, unchanging daylight. The center point of the day side, the place where the Sun sits directly overhead, is called the subsolar point. If you stood there, you'd see the Sun at the zenith, straight up, blazing down with full intensity. This would be the hottest place on the entire planet. Here's why. Right now, Earth's rotation means every part of the planet gets a break from the Sun. Even the hottest deserts cool down at night. Death Valley might hit 130 degrees Fahrenheit during the day, but at night it can drop to 70 or even lower. That nighttime cooling is essential. It prevents heat from building up indefinitely. But on a stopped Earth, the subsolar point never gets a break. The Sun beats down continuously, hour after hour, week after week. Heat accumulates. The ground absorbs sunlight, warms up and radiates that heat into the air. Normally, nighttime would let everything cool off, but there is no nighttime. The temperature just keeps climbing. How hot would it get? That's surprisingly hard to calculate precisely because it depends on so many factors: the albedo of the surface, cloud cover, atmospheric circulation. But we can make reasonable estimates. The subsolar point would likely reach temperatures well over 150 degrees Fahrenheit, possibly approaching 200 degrees or higher at the hottest spots. For reference, the highest temperature ever reliably recorded on current Earth is 134 degrees Fahrenheit in Death Valley. We're talking about conditions that make the hottest places on modern Earth seem almost pleasant by comparison. And it's not just surface temperature. As the ground heats up, it warms the air above it. Hot air rises, that's basic thermodynamics. So you'd have constant, powerful updrafts at the subsolar point. Air rising rapidly, cooling as it climbs, forming clouds, possibly creating perpetual thunderstorms. The dayside wouldn't just be hot and bright, it would be meteorologically chaotic. The rising air would pull in more air from the surrounding regions, creating surface winds that flow toward the subsolar point from all directions. Think of it like a permanent low-pressure system centered on the hottest spot on the planet. Winds converging, air rising, storms forming. And because there's no rotation to create the Coriolis effect and organize these winds into spiral patterns, you just have this constant inward flow, feeding the perpetual storm at the center. Now let's talk about water. Water is heavy and it takes a lot of energy to evaporate, but under constant, intense sunlight, evaporation would happen at a dramatic rate. Any body of water near the subsolar point, lakes, rivers, even oceans, would evaporate rapidly. The water vapor would rise into the atmosphere, adding humidity to an already hot environment. This is where things could get truly extreme. Water vapor is a greenhouse gas, a very effective one. The more water vapor in the atmosphere, the more heat it traps. More heat means more evaporation. More evaporation means more water vapor. This is what scientists call a positive feedback loop, and it's the same mechanism that made Venus the hellscape it is today. Venus. For those who haven't spent much time thinking about our nearest planetary neighbour, is what happens when a runaway greenhouse effect goes to its logical extreme. Venus receives about twice as much sunlight as Earth, but that's not why its surface temperature is 900 degrees Fahrenheit. The temperature is that high because the atmosphere is so thick, with carbon dioxide and other greenhouse gases, that heat cannot escape. The greenhouse effect on Venus is so extreme that the surface is hotter than Mercury, even though Mercury is closer to the Sun. Could Earth's day side turn into Venus? Probably not to that extreme, at least not quickly. Venus's runaway greenhouse effect took millions of years and involved factors specific to Venus, its proximity to the Sun, its lack of a magnetic field, the loss of its water. Earth has more going for it, but the principle is the same. Perpetual heating plus water vapor can create a feedback loop that drives temperatures much higher than you'd expect from sunlight alone. So the subsolar point and its surrounding region would likely be uninhabitable. Too hot for liquid water to remain on the surface for long. Too hot for most life as we know it. Certainly too hot for humans without serious technological assistance. But here's the interesting part. The day side isn't uniformly hot. The subsolar point is the hottest, but as you move away from it, toward the edges of the day hemisphere, the sun sits lower in the sky. Lower sun angle means the same amount of solar energy is spread over a larger area, which means less intense heating. It's the same reason why the poles are colder than the equator on current Earth, and why winter is colder than summer. So there would be a gradient, extremely hot at the centre, gradually cooling as you move away until you reach the Terminator, the boundary between day and night. And somewhere in that gradient there might be a habitable band, a zone where it's hot, yes, but not lethally so, where water could still exist in liquid form, where with adaptation life might persist. Let's think about what life in that habitable band might look like. You'd be living in perpetual daylight, but not the pleasant, moderate daylight of a spring afternoon, more like the harsh, intense light of high noon in a desert. The sun would hang in the sky at a constant angle, not overhead, but maybe 30 or 40 degrees above the horizon, depending on your latitude. Temperatures might range from 120 to 140 degrees Fahrenheit during what we might call the cooler periods. Though calling anything 120 degrees cool seems absurd, any exposed water would evaporate quickly. Rain would fall, but might evaporate before it hit the ground in the hottest areas. You'd need to live near underground water sources, or find ways to capture and store water from the wetter regions closer to the Terminator. Architecture would need to be completely reimagined. Buildings would need to be heavily shaded, with thick walls for insulation, minimal windows, and probably underground components. You'd want white or reflective surfaces to minimize heat absorption. Living underground would make a lot of sense. A few meters down, the temperature would be much more stable, buffered by the thermal mass of the Earth itself. If you had to venture outside during the hottest times, you'd need protective gear. Not quite a spacesuit, but serious heat-reflective clothing, cooling systems, and reliable hydration. Think of it like living in a permanent, extreme heat wave with no nighttime relief. But there's a silver lining, if you can call it that. The dayside wouldn't be completely static. Remember, Earth is still orbiting the Sun, which means seasons still exist. They'd be strange seasons, not the familiar cycle of changing day length we're used to, but rather a shifting of where the subsolar point falls on the planet's surface. Right now, Earth's axis is tilted 23.5 degrees relative to its orbital plane. That tilt is what gives us seasons. In summer, your hemisphere is tilted toward the Sun. In winter, it's tilted away. On a stopped Earth, that tilt would still exist, but instead of changing day length, it would change where the hottest spot is located. During the equivalent of Northern Hemisphere summer, the subsolar point would be somewhere in the northern tropics. 6 months later, during Northern Hemisphere winter, it would shift to the southern tropics. The hottest spot on the planet would migrate back and forth across the equator over the course of a year. This migration might make life slightly more manageable. If you lived in the habitable band and the seasons shifted the heat zone toward you, you might need to migrate or retreat underground. When the seasons shifted the heat away, conditions might become more tolerable. It's not the pleasant cycle of spring and fall we're used to, but it's something, a rhythm, a pattern to adapt to. Now let's think about what survives on the day side without human intervention. What plants and animals could adapt to these conditions? Plants are the foundation of almost all terrestrial life, and they need light to photosynthesize. In that sense, the day side has an advantage, unlimited sunlight, but they also need water and moderate temperatures. At the subsolar point, it's simply too hot. Most plants would die, their proteins would denature, their cell structures would break down, their leaves would desiccate in the intense heat. But in that habitable band we talked about, where temperatures are high but not lethal, you might see plants adapted to extreme conditions. Think of cacti and succulents, but more extreme. Deep root systems to access underground water. Thick, waxy cuticles to minimize water loss. Maybe reflective surfaces to reduce heat absorption. Small leaves or no leaves at all. Photosynthesis could happen in the stems. These plants would never experience night, which is actually a problem. Many plants do important work at night, repairing cellular damage, consolidating resources, preparing for the next day of photosynthesis. Constant photosynthesis without a break could be stressful. Plants might evolve internal circadian rhythms that don't depend on external light cues, allowing them to rest periodically even under constant illumination. Animals would face similar challenges. The hottest regions would be devoid of complex animal life, but in the habitable band you might find highly adapted creatures, small body sizes to minimize heat generation, nocturnal behavior patterns, even though there's no night, sheltering during the hottest periods, emerging when it's relatively cooler, except there is no cooler period in terms of light levels, so they'd have to rely on other cues or internal clocks. Desert animals on current Earth offer clues. Kangaroo rats, for example, never drink water. They get all their moisture from the seeds they eat and produce very concentrated urine to conserve water. Camels can tolerate significant dehydration and fluctuate their body temperature to reduce water loss. Dayside animals might evolve even more extreme versions of these adaptations. Insects might do surprisingly well. They're small, can burrow easily, and many are already adapted to extreme heat. Ants, termites, and beetles might thrive, creating underground colonies where temperature is more stable. They could emerge to forage on the surface briefly before retreating to the cool depths. And then there's the question of what happens to aquatic life. Deep oceans might actually be okay. Water has high heat capacity, meaning it takes a lot of energy to warm it up. The surface of the ocean on the day side would be warm, possibly very warm, but the deep ocean would remain relatively cool. Buffered by the sheer mass of water above it, deep-sea creatures might continue largely undisturbed, at least for a while. But surface and coastal ocean life would struggle. Coral reefs, which are already sensitive to temperature changes, would likely die off. Coral bleaching happens when water temperatures rise just a few degrees above normal perpetual heating, would be catastrophic for reefs. Fish that depend on those reefs would lose their habitat. The entire coastal ecosystem would need to reorganize around the new temperature regime. Algae and phytoplankton, which form the base of the ocean food chain, might actually increase their productivity due to constant sunlight. But they are also temperature sensitive, too hot, and they die. You'd likely see a shift in which species dominate. Heat-tolerant varieties would take over from species adapted to current temperatures. One fascinating possibility: life might concentrate along coastlines where ocean currents bring cooler water from the night side. These would be thermal oases, places where the water is warm but not lethally so, where the air is humid but not suffocating, where both terrestrial and aquatic life could find refuge. These transitional zones between the hot land and the less hot ocean might become biodiversity hotspots on the day side. So to sum up the day side, the center is uninhabitable, a scorched zone where water boils away and life cannot exist. Moving outward, you have a band of extreme but possibly survivable conditions, where highly adapted life, both natural and potentially human, could persist with difficulty. And at the edges, approaching the Terminator, conditions gradually become more moderate, though still harsh by current standards. The day side wouldn't be completely lifeless, but it would be dramatically reduced in biodiversity. Only the toughest, most heat-tolerant organisms would make it. And for humans, it would be a challenging frontier, survivable with technology and determination, but never comfortable. You'd be living on the edge of habitability, always aware that just a few 100 kilometers toward the center, conditions become lethal. It's a strange thing to think about, half your planet bathed in eternal light, slowly baking under a sun that never sets, but it helps us appreciate what we have now, the simple gift of nighttime, the cooling relief of darkness, the rhythm of day and night that makes Earth not just habitable, but hospitable. But if the day side is a world of endless light and heat, the night side is its opposite, a world of eternal darkness and cold so extreme it makes the Arctic seem tropical by comparison. Let's explore that frozen darkness next. If the day side is defined by too much energy, the night side is defined by too little. No sunlight, no warmth. Just an endless frozen darkness that makes Antarctica look like a tropical vacation. The center point of the night side, the anti-solar point, directly opposite the subsolar point, would be the coldest place on the planet. And when we say cold, we're not talking about a brisk winter morning or even a harsh Arctic night. We're talking about temperatures that approach what you'd find in the outer solar system. Here's the basic physics. Right now, every part of Earth receives sunlight for roughly half of each day. Even during that time, Earth is radiating heat into space. That's how planets cool down. But because every location gets regular doses of sunlight, the heating and cooling balance out more or less. Some places are warmer, some colder, but everywhere stays within a range that allows for liquid water and life. On a stopped Earth, the night side receives no solar input at all. Zero. It just radiates heat into space continuously, with nothing to replace that lost energy, and space is very good at absorbing heat. It's a perfect cold sink. Sitting at an average temperature of about 2.7 Kelvin, that's minus 270 degrees Celsius, or minus 454 degrees Fahrenheit, only a few degrees above absolute zero, the coldest temperature theoretically possible. Now, Earth wouldn't cool all the way down to 2.7 Kelvin. It has internal heat, from the decay of radioactive elements in its core and mantle, and from the residual heat of its formation. That internal heat constantly flows from the interior toward the surface. But internal heat is nothing compared to sunlight. The sun delivers about 1,360 watts of energy per square meter to Earth's surface. Geothermal heat provides maybe 0.09 watts per square meter. It's not even close. So without sunlight, the night side would cool and cool and cool until it reaches an equilibrium between the tiny amount of heat flowing from Earth's interior and the vast amount of heat radiating into space. That equilibrium temperature would be somewhere around minus 200 degrees Fahrenheit, possibly colder depending on atmospheric conditions. To put that in perspective, the coldest temperature ever recorded on current Earth is minus 128.6 degrees Fahrenheit at Vostok Station in Antarctica. The night side would be significantly colder than that. Cold enough that some rather remarkable things start to happen to the atmosphere itself. Our atmosphere is mostly nitrogen and oxygen, with smaller amounts of argon, carbon dioxide and water vapor. All of these gases have different freezing and condensation points. Water vapor freezes at 32 degrees Fahrenheit. We call that snow. Carbon dioxide freezes at minus 109 degrees Fahrenheit. On Mars, this is called dry ice, and it forms the polar ice caps there. Nitrogen, the most abundant gas in our atmosphere at 78%, liquefies at minus 321 degrees Fahrenheit and freezes at minus 346 degrees Fahrenheit. Oxygen liquefies at minus 297 degrees Fahrenheit and freezes at minus 362 degrees Fahrenheit. These are extraordinarily cold temperatures, but the night side of a stopped Earth might actually approach them, at least in its coldest regions. What would happen is this. As the night side cools, water vapor in the atmosphere would freeze and fall as snow. Then, as temperatures drop further, carbon dioxide would begin to freeze out. You'd have dry ice snow falling on the night side, accumulating in thick layers. Eventually, if it gets cold enough, even oxygen and nitrogen might start to condense and rain down, though whether the night side actually reaches those temperatures is debatable. The result would be a massive redistribution of Earth's atmosphere. Gases would migrate from the night side to the day side, pulled by temperature differences and pressure gradients. The night side would have much lower atmospheric pressure than the day side. In the very coldest regions, you might have almost no atmosphere at all. It would all be frozen on the ground. This creates an interesting problem. Lower atmospheric pressure means lower air density, which means less insulation. The thin atmosphere can't hold much heat, so temperatures drop even further, which causes more gases to freeze out, which lowers the pressure more. It's another feedback loop, but this time working in reverse of the day side's greenhouse effect. Instead of runaway heating, you get runaway cooling. The landscape of the night side would be alien in a way that's hard to imagine. Think of the most remote frozen place you've ever seen, the Arctic tundra, the Antarctic plateau, and make it colder and darker and more still. No wind because there's barely any atmosphere. No sound because sound needs air to travel. Just endless ice stretching in all directions under a sky full of stars that never move. Actually, that's not quite true. The stars would move, but very slowly, once per year, as Earth orbits the Sun. You'd see the constellations shift gradually over months, making a complete circuit annually. But on any given night, and every night is eternal on the night side, the stars would appear essentially fixed. The stars would be spectacular, though. With no light pollution, no atmospheric scattering from suspended particles, and perfectly clear skies, you'd see stars as clearly as astronauts see them from space. The Milky Way would be a brilliant band across the sky, distant galaxies visible to the naked eye. It would be one of the most beautiful night skies imaginable, even if appreciating it would require a very good heating system and a spacesuit. At the poles, you'd still have aurora, the northern and southern lights. Earth's magnetic field, assuming it's still functioning, would continue to channel charged particles from the solar wind toward the poles, where they'd collide with whatever atmosphere remains and create those familiar dancing curtains of light. The aurora would be one of the few dynamic, changing features of the night-side sky. Now let's talk about ice. We mentioned that water vapor would freeze and fall as snow. Over time, this would create ice sheets, massive accumulations of frozen water that would grow thicker and thicker as more snow falls. On current Earth, the Antarctic ice sheet is about 2 kilometers thick on average, reaching nearly 5 kilometers at its thickest point. That ice accumulated over millions of years. On the night side, you get something similar, but potentially even more extreme. All the moisture in the atmosphere on the night side would eventually freeze and settle. Water from the day side, evaporated by constant sunlight, would drift across the Terminator. As water vapor freeze on the night side and accumulate over time, you could end up with ice sheets kilometers thick, possibly thicker than anything we see on current Earth. Beneath these ice sheets, the surface would be crushed and preserved. Cities, forests, whatever existed before Earth stopped spinning, would be entombed in ice, frozen in time. It would be like the Arctic permafrost, which occasionally reveals perfectly preserved mammoths that died thousands of years ago, except on a planetary scale. But here's where it gets interesting. The night side wouldn't be uniformly cold. Just as the day side has a temperature gradient from the blazing center to the cooler edges, The night side has a gradient from the frozen centre to the less frozen edges, and just as the day side has internal heat from the sun, the night side has internal heat from Earth itself. Remember that geothermal heat we mentioned? The heat flowing from Earth's interior? It's weak compared to sunlight, but it's constant, and it's everywhere. About 0.09 watts per square metre on average, with higher values in geologically active areas, near volcanoes, hot springs, tectonic plate boundaries. On current Earth, geothermal heat is overwhelmed by solar heating, so we barely notice it except in specific locations like geysers or volcanic hot springs. But on the night side, where there's no solar heating to compete with it, geothermal heat becomes significant, not enough to keep the surface warm. The ice would still be there, thick and permanent, but deep underground where you're insulated from the frozen surface by kilometres of rock, geothermal heat could maintain temperatures that are not just survivable, but almost comfortable. This is the key to life on the night side. The surface would be essentially dead, too cold, too dark, too airless, but underground life could persist. Go deep enough, and you'd find temperatures around 50 or 60 degrees Fahrenheit, maybe warmer in geologically active areas. You'd have stable conditions, protected from the deadly cold above. On current Earth, we already know that life exists deep underground. Microbes have been found more than 5 kilometers down in mines and boreholes, living in tiny pores in the rock, feeding on minerals and geothermal energy. These are chemosynthetic organisms. They don't need sunlight or photosynthesis. They get their energy from chemical reactions, often involving hydrogen or methane released from rocks, or from the oxidation of minerals like iron or sulfur. On the night side, this kind of life could become the dominant form. Deep underground ecosystems, completely independent of sunlight, sustained by Earth's internal heat and chemistry. It wouldn't be a lush ecosystem, more like the sparse microbial communities found in deep mines or in the deep ocean near hydrothermal vents. But it would be life. Hydrothermal vents are actually a good analogy. In the deep ocean, where sunlight never reaches, there are places where hot, mineral-rich water flows out of cracks in the seafloor. These vents support entire ecosystems, bacteria that oxidize sulfur or methane, tube worms that harbour those bacteria in their tissues, and various other creatures that feed on the bacteria, or each other. These ecosystems are completely independent of photosynthesis. They run on geothermal energy and chemistry. The night side could have something similar, but on land. Anywhere with geothermal heat, old volcanic systems, tectonic boundaries, areas where heat flow is higher than average. You could have networks of caves and caverns where water is liquid, where minerals are available, and where chemosynthetic life could thrive. For humans, the night side would actually be a more plausible refuge than the day side in some ways. The technology needed to survive underground on the night side is similar to the technology we'd need in many other extreme scenarios: insulation, artificial lighting, closed-loop life support, food production without sunlight. We've talked about this before in the context of the sun-disappearing hydroponics, LED grow lights, recycling systems. It's all technically possible with enough energy. And on the night side, you'd have that energy in the form of geothermal power. Drill down to where the rocks are hot, pump water through, and you get steam to drive turbines. It's clean, renewable, and available everywhere on the planet if you go deep enough. Some areas would be better than others. Iceland, with its abundant volcanic heat, would be an ideal location even on the frozen night side. But in principle, you could establish underground colonies anywhere. These colonies would be dark except for artificial light. Quiet because there's no weather, no wind, no rain. The temperature would be controlled, the air recycled. You'd grow food in underground farms, never seeing the sun. It would be a strange existence, almost like living in a cave or a submarine for your entire life, but it would be survivable. Children born in these colonies would never see sunlight. They'd know it only as a myth, a story about the burning sky on the other side of the world. Their concept of outside would be the frozen wasteland above, a place you go only with extreme protective gear, briefly, before returning to the warmth and safety of the depths. The deep earth would be home. One advantage of the night side: no weather. Weather requires energy, and on the night side there's very little energy in the atmosphere. No sun to drive convection, no temperature differences to create wind. It would be eerily still. The most stable, predictable environment on the planet, boring perhaps, but safe from storms. The night side would also have access to resources that the day side lacks. All those frozen gases we mentioned, the atmosphere that condensed and fell as snow. That's not just ice. That's nitrogen, oxygen, carbon dioxide, all in solid or liquid form sitting on the surface. If you could mine it, and why not? It's just lying there. You'd have all the raw materials you need for life support systems. Extract the oxygen, warm it up, and you have breathable air. The frozen nitrogen could be used for fertilizer or industrial processes. In a strange way, the night side might be the easier place for a technological civilization to survive. It's harsh, yes, but it's predictable. No scorching heat to manage, no violent weather, no runaway greenhouse effects. Just cold and dark, which are problems we know how to solve. Insulation and artificial light. That's basically it. But it would come at a psychological cost. Humans evolved under sun and sky. We have circadian rhythms tuned to daylight. We feel energized in the morning, tired at night, happier on sunny days, living in permanent darkness underground with only artificial light. That would take adaptation. Not impossible, but not natural either. People who work in submarines or at Antarctic research stations during the winter months sometimes experience seasonal affective disorder or circadian disruption, even with limited light deprivation. Imagine that, but permanent. You'd need to carefully manage light exposure, maintain strict schedules, possibly use medications or therapies to keep people psychologically healthy. It would be a challenge, though likely a manageable one. The night side would also be the best place for astronomy, paradoxically. With no atmospheric interference, no light pollution and stable conditions, you could build incredible telescopes on the surface. They'd need to be heated and maintained, but the viewing conditions would be unparalleled. You could see the universe with a clarity that Earth-based astronomy has never achieved. And there's something poetic about that. A civilization living in the dark, sustained by the Earth's inner warmth, spending their time studying the stars, looking outward from a frozen world toward distant galaxies, seeking light in the darkness, even if it's light from billions of years ago, from suns they'll never feel. So the night side, frozen, dark, but not dead. Life could exist in the depths, sustained by geothermal heat and chemistry. Humans could survive with the right technology, building underground cities lit by artificial suns. It would be challenging, strange, requiring complete adaptation to a sunless existence. But it would be possible. And yet most life, most humans, if they survived at all, wouldn't choose to live in the extremes of perpetual day or perpetual night. They'd seek out the middle ground, the place where the sun neither burns nor abandons, the narrow ring between light and dark where both are present, neither dominant. They'd seek the Terminator zone, the eternal twilight, and that's where we're going next. Between the burning day and the frozen night lies a narrow band of perpetual twilight. This is the Terminator zone, named after the line that separates day from night on any celestial body. On current Earth, the Terminator sweeps around the planet once every 24 hours, bringing sunset to some places and sunrise to others. But on a stopped Earth, the Terminator stays put. It becomes a place, a ring circling the entire planet where the sun sits forever on the horizon. This would be the most important piece of real estate on the planet. The only zone where conditions are neither too hot nor too cold, where you get some light, but not too much, where life as we know it could realistically persist without extreme technological support. If humanity were to survive on the surface of a stopped Earth, this is where we'd gather. Let's start with what it would actually look like to stand in the Terminator zone. The sun would be visible, but just barely. Depending on exactly where you're standing within the zone, the sun might be sitting right on the horizon, or maybe a few degrees above it. The light would be similar to what you experienced during the last few minutes before sunset, or the first few minutes after sunrise. That soft golden light that photographers call the golden hour. Except this golden hour would never end. The sun wouldn't climb higher, wouldn't set lower. It would just sit there, casting long shadows that never move, painting the sky in perpetual shades of orange and red and pink. The side of the sky toward the day side would be brighter, warmer in colour. The side toward the night side would be darker, fading to deep blue and eventually to black where the stars become visible. It would be beautiful in a strange, static way, like living inside a permanently paused sunset, but it would also be disorienting. On current Earth, we use the sun's position to tell time and direction. The sun rises in the east, sets in the west, reaches its highest point at noon. In the Terminator zone, the sun doesn't move, or moves so slowly over the course of a year that you wouldn't notice. On any given day, you'd need other cues to track time. Maybe the slow shift of constellations in the night sky. Maybe just clocks and calendars. The width of the Terminator zone would depend on how we define it. If we're talking about the area where the sun is within a few degrees of the horizon, it might be a few 100 kilometers wide. If we're generous and include areas where the sun is up to 10 or 15 degrees above the horizon, still providing relatively low-angle light, the zone could be 1,000 kilometers wide or more. That's a lot of space. A ring around the entire planet, covering millions of square kilometers. But within that ring, not all locations would be equal. The Terminator zone would have its own internal climate zones, varying by latitude. Near the equator, where the day side is hottest and the night side is coldest, the Terminator zone would experience stronger temperature gradients. The air would be more turbulent with stronger winds. At higher latitudes, closer to the poles, the gradients would be gentler, conditions more stable. Let's talk about temperature. The Terminator zone wouldn't be uniformly temperate. The side closer to the day side would be warmer, maybe 80 to 100 degrees Fahrenheit in the warmest areas. The side closer to the night side would be cooler, perhaps 40 to 60 degrees Fahrenheit, and somewhere in between you'd have a sweet spot, a band where temperatures hover around 60 to 75 degrees Fahrenheit. Comfortable, livable. The kind of temperature where you could exist outside without special equipment, at least for a while. Now, of course, these are rough estimates. The actual temperatures would depend on atmospheric circulation, cloud cover, the presence of oceans nearby, and a dozen other factors. But the basic principle holds. The Terminator zone would have a temperature gradient from warmer to cooler, and somewhere in that gradient would be conditions suitable for life. Water would be available in the Terminator zone, at least in some areas. Any water on the night side would be frozen solid, But in the Terminator zone, temperatures would be high enough for liquid water. You'd have lakes, rivers, maybe even small seas depending on the local geography. Water vapor from the day side would drift across the Terminator as humid air, condense in the cooler temperatures and fall as rain or mist. The Terminator zone would be where the water cycle still functions, at least partially. This makes the Terminator zone critical for life. Water, moderate temperatures and some light. Those are the basic requirements for photosynthesis, and by extension for most terrestrial ecosystems. Plants could grow here. Not easily, perhaps, and not in the same abundance as on current Earth, but they could grow. The light levels would be the main challenge for plants. Photosynthesis requires light, but the intensity matters. Full sunlight at noon provides around 100,000 lux twilight conditions. The kind you'd get in the Terminator zone might provide only 1,000 to 10,000 lux, depending on how high the sun is above the horizon and how clear the sky is. That's enough for photosynthesis, but barely. Plants would need to adapt. You might see plants with larger leaves to capture more light, darker pigments perhaps to absorb more of the available spectrum, or plants that are simply very efficient at low light levels, like the shade-adapted plants you find on the forest floor in current Earth's temperate and tropical forests. Mosses, ferns and certain grasses might do well. Trees could grow, though they'd probably be smaller and more widely spaced than in current forests. Agriculture would be possible in the Terminator zone, but it would require careful crop selection. You'd want plants that can tolerate low light, cool temperatures, and the constant twilight conditions. Root vegetables like potatoes and carrots might work, leafy greens like lettuce and spinach, certain grains like barley or oats, which are adapted to cooler climates. You wouldn't be growing corn or wheat on a large scale, but you could probably produce enough food to support a population, especially with supplemental artificial lighting in greenhouses. Animals would face their own challenges. The constant twilight would disrupt normal circadian rhythms. Most animals on current Earth are either diurnal, active during the day, or nocturnal, active at night. But in the Terminator zone, there is no day or night, just perpetual dim light. Animals would need to develop new patterns of behavior. Some species might maintain internal clocks, sleeping and waking on a roughly 24-hour cycle, even without external light cues. Others might abandon that pattern entirely, becoming active whenever they're hungry, or need to migrate, resting whenever they're tired. You'd probably see a shift toward cathemeral behavior, being active at irregular intervals throughout the day and night. That's already how some tropical animals behave in regions where day length doesn't vary much. Predators and prey would both need to adapt. In current ecosystems, many predators hunt at dawn or dusk when light levels are low, giving them an advantage. In the Terminator zone, it's always dawn or dusk. Prey animals would need to be constantly vigilant. Predators would lose their temporal advantage. The evolutionary pressures would be fascinating to watch, though we'd need thousands of years to see how it all shakes out. Birds would have an interesting time. Many bird species migrate based on day length and sun position. In the Terminator zone, those cues would be constant. Birds might still migrate, but they'd have to rely on other signals. Temperature changes, food availability, internal clocks. Or they might abandon migration entirely, becoming permanent residents of whatever region suits them best. Now let's talk about wind, because the Terminator zone would be one of the windiest places on Earth. Remember that temperature drives wind. Hot air rises, cool air sinks, and air flows from high pressure to low pressure. On a stopped Earth, you'd have massive temperature differences between the day side and the night side, and the Terminator zone is where those two air masses meet. Hot air from the day side would rise and flow toward the night side at high altitude. Cool, dense air from the night side would flow toward the day side at low altitude, and all of this air has to pass through the Terminator zone. You'd have constant winds, probably quite strong. Sustained speeds of 30 to 50 miles per hour wouldn't be unusual, with gusts potentially much higher. These winds would blow in a consistent direction, always from the cold side toward the warm side. No Coriolis effect to deflect them, remember. Earth isn't spinning. Just straight-line flow driven by temperature differences. This consistency would actually be useful. You'd know exactly where the wind is coming from and could design your buildings, windmills and farms accordingly. And speaking of windmills, the Terminator zone would be ideal for wind power. Constant, predictable winds, that's a renewable energy engineer's dream. You could line the Terminator with wind turbines, generating power continuously, without having to worry about variable wind conditions. Between wind power and geothermal energy from the deeper layers, the Terminator zone could be completely energy independent. The constant wind would shape the landscape. Trees would grow leaning away from the wind, their branches streaming like flags. Erosion patterns would be predictable. Dunes would form and migrate in consistent directions. The Terminator zone would develop its own characteristic geography, shaped by the one-way wind. Human civilization in the Terminator zone would need to be designed around these conditions. Buildings would need to be aerodynamic, low profile, oriented to minimize wind resistance. Large windows on the leeward side, small or no windows on the windward side. Thick walls for insulation. Remember, one side of your building faces toward the day side's heat, the other toward the night side's cold. Architecture might end up looking like a fusion of desert and Arctic designs. Heat-reflective materials to handle warmth from the day side, excellent insulation to keep out cold from the night side, wind-resistant shapes to handle the constant breeze, solar panels on the day-facing side to capture that perpetual golden hour light, water collection systems to harvest rain and condensation. Cities in the Terminator zone would probably be elongated, stretching north-south along the band rather than east-west across it. That way, residents could easily move to warmer or cooler areas depending on their needs or the season, because yes, seasons would still exist in the Terminator zone, just not the kind we're used to. Remember Earth's axial tilt. Over the course of a year, the subsolar point migrates from the northern tropic to the southern tropic and back. This means the Terminator line shifts too. In northern summer, it moves north. In northern winter, it moves south. If you're living in the Terminator zone at, say, 30 degrees latitude, you might find that during summer conditions become warmer as the day side shifts closer to you. During winter, conditions cool as the night side approaches. This seasonal shift would be the main temporal pattern in Terminator zone life. Not a shift in day length, the light stays constant, but a shift in temperature and wind patterns. Civilizations might migrate seasonally, following the optimal temperature band, or they might have seasonal homes, spending the warm months in one location and the cool months in another. Nomadic cultures would make a lot of sense. Infrastructure would need to accommodate this migration. Roads and rail lines running north-south along the Terminator zone. Seasonal settlements designed to be occupied for half the year and then abandoned. Or, alternatively, buildings designed with flexible climate control, able to handle both the warmer and cooler extremes of the seasonal cycle. The Terminator zone would also be where weather happens. Weather requires energy and temperature differences, and the Terminator zone has both warm, moist air from the day side colliding with cool, dry air from the night side. That's a recipe for storms. You'd have frequent cloud formation, precipitation, possibly thunderstorms in the more energetic parts of the zone. But these wouldn't be organized storm systems like hurricanes or typhoons, which require the Coriolis effect to spin up. Without Earth's rotation, you'd have more chaotic, localized storms, convective cells forming where the temperature gradient is steepest, squall lines moving along the terminator, rain showers, maybe hail in the cooler areas, not organized, but not entirely random either. There would be patterns based on geography and season. Water resources in the terminator zone would be surprisingly good. The constant flow of moist air from the day side would condense in the cooler terminator temperatures, creating a steady supply of rainfall. Rivers would flow from the terminator toward both the day and night sides, though most would probably flow toward the night side, where lower pressure creates a pull. You'd want to build your settlements near these rivers, just as civilizations have always clustered near water sources. One challenge: navigation. On current Earth, we use the sun's position to find direction. In the terminator zone, the sun's position is constant. You'd need to rely on other methods: compass bearings, star positions, landmarks, or maybe the wind itself would become a directional reference. The wind always blows from the night side toward the day side, so if you know which way the wind is blowing, you know which direction you're facing. It's a reliable compass, assuming you remember which is which. Psychologically, living in the terminator zone would be easier than living in the extremes. You'd have some light, which is important for mental health and circadian regulation. The temperature is moderate, which is comfortable. You'd see the sky, see weather patterns, experience something resembling the natural world. It wouldn't be normal, but it would be closer to normal than the eternal oven of the day side or the frozen tomb of the night side. That said, the constant twilight would take adjustment. Humans evolved with clear day-night cycles. We feel wakeful in bright light, sleepy in darkness. In the terminator zone, the light never changes. You'd need to create artificial day-night cycles indoors, using lighting that mimics sunrise and sunset. Bedroom windows might have heavy curtains to create darkness for sleeping. Workspaces might use bright artificial light to maintain alertness. You'd be imposing structure on an environment that naturally has none. Children growing up in the terminator zone would have a unique perspective. They'd never see a true sunrise or sunset. The sun would always be in the same position. They might not understand what adults mean when they talk about the sun rising in the east and setting in the west. To them, the sun would be a fixture, like a lamp that's always on the stories of Earth's rotation, of spinning through space at 1,000 miles per hour. Would seem like mythology. But they'd understand wind in a way that current humans don't. Wind would be as constant as gravity, always there, always from the same direction. They'd know which side of every building is sheltered, which side is exposed. They'd design kites and windmills and sails instinctively. Wind would be their companion, their resource, their constant reminder that their world is divided between heat and cold, light and dark. The terminator zone would likely become the center of whatever civilization emerges on a stopped Earth. It's the compromise zone, the place where both day and night dwellers could meet. A person from the day side could travel to the terminator, gradually acclimating to lower temperatures and dimmer light. A person from the night side could make the opposite journey. The terminator would be neutral ground, the place where extremes meet. Trade routes would run through the terminator zone. Goods from the day side, perhaps minerals extracted from the hot, dry regions, would be traded for goods from the night side, maybe ice or frozen gases. The terminator would host the markets, the meeting places, the diplomatic centers. It would be the economic and cultural heart of the planet, even if its total land area is just a fraction of either hemisphere. In a way, the Terminator zone represents balance, between too much and too little, between light and darkness, between heat and cold. It's the edge between extremes, the middle way, the place where life finds its footing when the comfortable centre is no longer available. And if humanity were to survive on a stopped Earth, this is where we'd make our stand. In the perpetual twilight, between the sun that never sets and the night that never ends. Evolution doesn't stop when conditions change, it accelerates. When the environment shifts dramatically, organisms either adapt, migrate, or go extinct. On a stopped Earth, we'd see all three happening simultaneously, at scales both massive and microscopic. Life, in its stubborn determination to persist, would find ways forward that we can barely imagine. Let's start with the most fundamental change, the death of circadian rhythms as we know them. Almost every organism on Earth, from bacteria to whales, operates on an internal clock, roughly synchronized to the 24-hour day. This isn't just about sleep. Circadian rhythms control when genes are expressed, when hormones are released, when cells divide, when flowers open, when insects emerge. The entire machinery of life is tuned to the cycle of day and night. On a stopped Earth, external day-night cues disappear. On the day side, it's always bright. On the night side, it's always dark. In the Terminator zone, the light never changes. So what happens to those internal clocks? The short answer is they'd persist, at least initially. Circadian rhythms are so deeply embedded in biology that they continue even without external cues. Put a person in a cave with no light, and they'll still sleep and wake on roughly a 24-hour cycle. Plants will still open and close their leaves, mice will still be active during their usual hours. The clocks keep ticking even when there's no sun to set them by. But over generations, without the reinforcement of day-night cycles, those clocks would drift. Some organisms might maintain their rhythms. Evolution is conservative, and if a trait isn't actively harmful, it can persist for a long time. Others might lose their rhythms entirely, becoming arrhythmic, active, and resting based on immediate needs rather than time of day. In the Terminator zone, you might see organisms develop new rhythms based on other cues. Temperature fluctuations from seasonal shifts, wind patterns, social synchronization with other members of their species. Biology is remarkably flexible. If there's a pattern to be found, evolution will find it and build a rhythm around it. Now let's talk about plants, because they're the foundation of most terrestrial ecosystems, and they'd face some unique challenges on a stopped Earth. Plants need light for photosynthesis, but they also need periods of rest. On current Earth, plants do important metabolic work at night, repairing damaged DNA, consolidating resources, preparing for the next day of growth. Constant photosynthesis without a break is actually stressful for most plants. On the day side, plants would need to evolve ways to rest even under constant illumination. Some current Earth plants already do this in the Arctic summer, where the sun never sets for months. They maintain internal rhythms that tell them when to photosynthesize actively and when to dial it back, even though the light is constant. Dayside plants would need to perfect this strategy. You might see plants with movable leaves that fold up periodically to reduce light exposure, giving the plant a chance to rest. Or plants that alternate which leaves are active, using half their foliage for photosynthesis while the other half recovers, or plants with reflective surfaces that they can adjust to control how much light they absorb. Evolution would experiment with many solutions, and the most successful would proliferate. The colour of plants might change too. On current Earth, most plants are green because chlorophyll, the primary photosynthetic pigment, reflects green light and absorbs red and blue. But chlorophyll isn't the only option. Some bacteria use different pigments that absorb different wavelengths. On a stopped Earth, particularly in the Terminator zone where light levels are low, you might see plants evolving darker pigments to capture more of the available light deep purple or black leaves, absorbing across the entire visible spectrum. Or the opposite, on the day side, where light is intense and heat is a problem, plants might evolve lighter colours to reflect more light and reduce heat absorption. Silver or white leaves, maximising reflection while still capturing enough light for photosynthesis. You'd end up with a planet where plant colour varies dramatically by region. Dark plants in the Terminator zone, light plants in the habitable band of the dayside. Underground, in the darkness of the nightside's depths, plants wouldn't exist at all. You can't photosynthesize without light, but fungi would thrive. Fungi don't need light, they're decomposers, breaking down organic matter and absorbing nutrients. In a sunless underground ecosystem, fungi would take the role that plants normally fill, becoming the primary producers in a sense, though they'd be producing by recycling rather than creating new organic matter from sunlight. And that brings us to chemosynthesis, which we've mentioned before. This is the process by which organisms derive energy from chemical reactions rather than sunlight. On current Earth, chemosynthetic bacteria live in some of the most extreme environments. Deep ocean vents, underground aquifers, hot springs. They oxidize minerals like iron, sulfur, or hydrogen, extracting energy from those reactions. On the night side, chemosynthetic bacteria would become the base of the food chain. In caves warmed by geothermal heat, where water is liquid and minerals are abundant, you'd have bacterial mats coating the rocks. These bacteria would support small invertebrates, worms, arthropods, maybe even specialized fish if there are underground water systems. It would be a slow, sparse ecosystem, nothing like the lush forests or coral reefs of current Earth, but it would be an ecosystem nonetheless. Animals would face their own adaptive challenges. Let's start with vision. On current Earth, most animals have eyes adapted to daylight or low-light conditions. Diurnal animals, active during the day, tend to have eyes optimized for color vision and bright light. Nocturnal animals have large eyes with lots of rod cells, optimized for seeing in darkness. In the Terminator zone, where light levels are perpetually low, you'd expect animals to evolve nocturnal-type eyes, large, sensitive, good at gathering every available photon, but they'd also need to see in color, at least to some degree, because that perpetual twilight still has color. You might end up with animals that have unusually large eyes with a mix of rods and cones, capable of both high sensitivity and color discrimination. On the day side, animals in the habitable band would need protection from intense light. Dark-colored eyes, perhaps, with built-in shading mechanisms, or eyes that can constrict their pupils to almost nothing, like cats, but more extreme. Some animals might become primarily subterranean, emerging only briefly to forage before retreating to cooler, darker burrows. On the night side, particularly in the deep underground ecosystems, eyes would become useless. Complete darkness makes vision impossible no matter how good your eyes are. Animals would lose their eyes over generations, just as cavefish have lost theirs on current Earth. They'd rely instead on other senses: touch, smell, echolocation, perhaps even the ability to sense heat or vibrations through the ground. Thermoregulation would be critical everywhere. On the day side, animals would need ways to avoid overheating: large ears like elephants have to radiate heat, light-coloured fur or scales to reflect sunlight, the ability to reduce metabolic rate during the hottest periods, or, as we mentioned, going underground where temperatures are more stable. On the night side, the challenge is staying warm. Thick insulation, fur, fat layers, feathers, high metabolic rates to generate heat, or, again, living underground where geothermal warmth keeps things livable. Surface life on the night side would be extremely limited. Maybe some extremophile bacteria or specialized insects, but not much else. In the Terminator zone, temperature regulation would be more manageable, but animals would still need to deal with the constant wind and the temperature gradient. Animals might migrate seasonally not for day length, but to follow their preferred temperature band as the seasons shift. You'd have herds moving north and south along the Terminator, following the sweet spot of moderate temperatures year after year. Migration is an interesting question, actually. On current Earth, many animals migrate based on day length, using the changing hours of sunlight as a signal to move. Without that cue, migration would need to be triggered by other factors: temperature, food availability, or purely internal timing. Some species might continue to migrate on an annual cycle based on circadian clocks scaled up to circannual rhythms. Others might abandon migration entirely if their environment is stable enough. Birds would have a particularly interesting time. Flight is energetically expensive, and many birds rely on thermal updrafts, rising columns of warm air to gain altitude without flapping. On the day side, especially near the subsolar point, updrafts would be strong and constant. Birds could soar for hours, barely moving their wings, but in the Terminator zone, and especially on the night side, updrafts would be rare or absent. Birds might evolve to be stronger flyers, relying more on muscle power and less on thermals. Or you might see a split. Birds on the day side that are excellent soarers with large wingspans, and birds in the Terminator zone that are more compact, powerful flyers. Different environments, different evolutionary pressures, potentially leading to different species over time. Aquatic life would have its own adjustments to make. We mentioned earlier that deep oceans would be relatively stable, buffered by the thermal mass of water. But surface and coastal waters would be affected by the temperature extremes. On the day side, surface waters would be warm, possibly very warm. On the night side, they'd be cold, potentially freezing over. Fish and other aquatic animals would migrate with the temperature zones they prefer. Cold water species would dominate near the night side, warm water species near the day side. The Terminator zone would have the most diversity, with species from both extremes meeting and potentially interbreeding. Phytoplankton, the microscopic plants that form the base of the ocean food chain, would face challenges. They need sunlight for photosynthesis, which means they can only survive in the dayside and Terminator zone oceans. On the night side, the ocean surface would be barren of photosynthetic life. But deep ocean ecosystems that rely on chemosynthesis at hydrothermal vents would continue undisturbed. They'd become the only marine ecosystems on the night side. Now let's think about humans specifically, because our evolutionary adaptations would be different from other animals. We adapt primarily through culture and technology, not biological evolution, but over many generations, biological changes would still occur. In the Terminator zone, where most humans would probably live, you might see people evolving eyes better adapted to low light, larger eyes, more sensitive to dim illumination, or perhaps enhanced night vision, similar to what some nocturnal animals have. These changes would take thousands of generations, but they'd happen. Skin color might change too. On current Earth, skin color is largely determined by latitude. Darker skin near the equator, where UV exposure is high. Lighter skin at higher latitudes, where UV is lower and vitamin D synthesis is more challenging. On a stopped Earth, the day side would have constant UV exposure, favoring very dark skin. The night side would have no UV at all, potentially favouring very light skin to maximise whatever vitamin D synthesis is possible from artificial light or dietary sources. The Terminator zone would be intermediate, but with an interesting twist. One side of your body would face the day side, receiving more light. The other side would face the night side, receiving less. You might end up with people who have asymmetric skin tone, darker on one side, lighter on the other. That seems unlikely to be strongly selected for, but is a fun thought experiment. More realistically, Terminator Zone humans would probably just wear protective clothing and use sunscreen on the day-facing side, negating any evolutionary pressure for skin color changes. That's the thing about human evolution. Once you have culture and technology, biological evolution slows down because you can modify your environment instead of waiting for your genes to catch up. Sleep patterns would definitely change. Without natural day-night cycles, humans would need to impose artificial ones, but those cycles might not be 24 hours. Some research suggests that in the absence of external cues, humans naturally drift toward a 25-hour cycle. On a stopped Earth, without the tyranny of the sun's schedule, societies might adopt whatever sleep cycle works best for them: 25 hours, 30 hours, maybe even shorter cycles with multiple sleep periods per day. This would have cultural implications. Different settlements might adopt different cycles, making coordination difficult. Trade caravans arriving when the local population is asleep. Diplomatic meetings requiring careful scheduling. Or maybe a universal standard would emerge, imposed for practical reasons even if it doesn't match anyone's natural rhythm. Children born on a stopped Earth would develop differently from their ancestors. Without ever experiencing true day and night, sunrise and sunset, they'd have a different relationship with time. The concept of a day might become abstract, defined by clocks rather than experienced through the sun's movement. They'd learn about Earth's rotation as history, a strange feature of the old world that their grandparents remember but they never knew. And yet, they develop their own sense of rhythm. The seasonal migration of the Terminator Zone, the constant wind, the slow shift of stars over the course of a year. Humans are pattern-finding creatures. We'd find new patterns, new cycles, new ways to mark time and give structure to our lives. Psychologically, adaptation might be the hardest part. We evolved to need sunlight, to feel energized by bright light and drowsy in darkness, living in constant twilight, or underground in artificial light, or under the relentless glare of the dayside. All of these would be psychologically challenging. Depression, anxiety, sleep disorders, all would likely be more common. But humans have lived in extreme conditions before and found ways to cope. Antarctic researchers spend months in darkness during the polar night. Submariners spend months underwater with only artificial light. Miners work deep underground. It's not easy, but it's possible. With proper lighting schedules, therapeutic interventions, and social support, humans could psychologically adapt to life on a stopped Earth. The bigger question is whether we'd want to. Adaptation isn't just about survival, it's about quality of life. Yes, humans could survive in the Terminator Zone or underground on the night side, but would it be a life worth living? Would we thrive, or merely persist? That depends on what we make of it. Humans have proven remarkably resilient and creative. We've built civilizations in deserts, in Arctic tundra, on tiny islands, in mountain valleys. We've adapted to every climate zone Earth has to offer. A stopped Earth would be more challenging than any of those, but the principle is the same. Find the resources, build the infrastructure, create a culture that makes life not just possible, but meaningful. The adaptations would be profound, not just biological, but cultural, technological, psychological. we'd become a different kind of human, shaped by the strange new world we'd found ourselves in. Not better or worse necessarily, but different. Adapted to perpetual twilight, or eternal day, or frozen darkness. Children of a stopped earth, making the best of circumstances that should have been impossible. Evolution doesn't care about comfort, it only cares about survival and reproduction. And life, given even the smallest opportunity, finds a way on a stopped earth. That way would be strange and difficult and beautiful in its strangeness. Life adapting to stillness, thriving in conditions that seem inimical to thriving. Persisting, because that's what life does. It's humbling, in a way, to realize that life is more resilient than we imagine, that even in this impossible scenario, with Earth's rotation ceased and half the planet frozen, life would find a path forward. Not the same life, not the same ecosystems, but life nonetheless. And perhaps that's the real lesson here. Not that stopping Earth's rotation would be survivable, it probably wouldn't be, at least not for most of us, but that life is stubborn, that evolution is creative, that given time and opportunity, living things adapt to almost anything. Now, having explored how life would adapt, let's take a step back and look at the physics more carefully, because there are some deeper questions about what happens when a planet stops spinning. Questions about magnetic fields, atmospheres, and whether this scenario could even play out the way we've imagined. We've explored what life on a stopped Earth might look like, but there are some deeper physical questions we need to address. Questions about tidal locking, atmospheric circulation, ocean distribution, and the magnetic field. These aren't just abstract physics problems. They determine whether the scenario we've been imagining could actually work the way we've described. Let's start with tidal locking, because we've been assuming that a stopped Earth would have one face permanently toward the Sun and one face permanently away. But would Earth actually become tidally locked to the Sun if it stopped rotating? Tidal locking is a real phenomenon. The Moon is tidally locked to Earth, which is why we always see the same face of the Moon. It happened because Earth's gravity created tidal bulges on the Moon, and the friction from those bulges gradually slowed the Moon's rotation until one face permanently faced Earth. The process took millions of years, but it was inevitable given enough time. For Earth to become tidally locked to the Sun, the same process would need to happen in reverse. The Sun's gravity would need to slow Earth's rotation until one face always pointed toward the Sun. But here's the problem. Earth is much farther from the Sun than the Moon is from Earth, and tidal forces weaken rapidly with distance. Specifically, they weaken with the cube of the distance, which means they get weak very quickly. The Sun's tidal force on Earth is about half the strength of the Moon's tidal force on Earth. That's enough to create ocean tides, but it's very weak for slowing rotation. At Earth's current distance from the Sun, tidal locking would take billions upon billions of years, probably longer than the Sun will remain a stable star. In other words, it's not going to happen naturally before the Sun expands into a red giant and engulfs Earth entirely. So in our scenario where Earth's rotation suddenly stops, we wouldn't actually get perfect tidal locking. Instead, we'd have something stranger, a planet that doesn't rotate relative to the stars at all. This means the Sun would slowly drift across the sky over the course of a year as Earth orbits. One full day would equal one full year. Imagine standing on the equator of this stopped Earth. At the start of the year, the Sun is directly overhead. It's noon. Over the next 3 months, the Sun slowly moves westward across the sky, taking about 90 days to reach the horizon. Then it dips below the horizon, and you experience 3 months of night. Then it rises again in the east, taking another 3 months to climb back to its zenith. The entire cycle takes a year, and the sun's position tells you what season it is. This would actually moderate some of the extreme conditions we've been describing. Instead of having one hemisphere in permanent day and one in permanent night, you'd have day and night slowly cycling around the planet over the course of a year. Each location would get 6 months of daylight and 6 months of darkness, which is actually what happens at the poles on current Earth. But for the sake of our thought experiment, let's stick with the tidally locked scenario. It's cleaner conceptually, it creates more dramatic conditions, and it helps us explore the extremes. Just know that in reality, if Earth's rotation stopped, things would be slightly less extreme than we've been imagining, though still pretty catastrophic. Now let's talk about the atmosphere, because atmospheric circulation is crucial to whether life could survive on a stopped Earth. We've described wind blowing constantly from the night side toward the day side, driven by temperature differences. But would the atmosphere remain stable, or would it all migrate to one side? This is a genuine concern. If the night side gets cold enough, and we've established it would get very cold, gases start to freeze out of the atmosphere. Water vapour freezes first, then carbon dioxide, and eventually even nitrogen and oxygen if it's cold enough. All these frozen gases would accumulate on the night side as snow and ice. Meanwhile, on the day side, the atmosphere would be heated and expand, creating high pressure. This pressure difference would drive winds from day to night, but as gases freeze on the night side and fall out of the atmosphere, they're no longer part of the circulation. They're locked up as ice. The question is, does this process run away, stripping the atmosphere entirely, or does it reach an equilibrium where some atmosphere remains in circulation? The answer probably depends on how cold the night side actually gets and how much atmospheric mixing occurs. If there's sufficient circulation, if winds are strong enough to keep moving gas from day to night and back again, then the atmosphere might remain mostly intact. The night side would have lower pressure than the day side, and some gases would be frozen out, but the bulk of the atmosphere would keep circulating. If circulation is weak, or if the night side is extremely cold, you could end up with most of the atmosphere frozen on the night side, leaving the day side with very thin air. This would make life much harder on the day side. Less atmospheric insulation means more extreme temperature swings, more radiation exposure, less pressure for liquid water. Most models suggest that circulation would maintain at least some atmosphere on both sides, but it's not certain. This is one of those areas where we'd need detailed computer simulations to know for sure, and even then, the answer might depend on specifics like Earth's orbital distance, axial tilt, and the composition of the atmosphere. For our purposes, let's assume the optimistic scenario. Circulation is strong enough to maintain atmosphere on both sides, though with reduced pressure on the night side. This allows for the Terminator zone ecosystem we've been describing, with winds constantly flowing but atmosphere available everywhere. Next question. What happens to the oceans? Water is heavy, and on a stopped Earth it would redistribute based on gravity and temperature. We mentioned that tsunamis would be a problem during the initial stop, but after things settle, where does the water end up? On current Earth, the oceans are held in basins by gravity and the shape of the seafloor, but Earth's rotation creates a centrifugal force that causes water to bulge slightly at the equator. If rotation stops, that bulge would disappear, and water would redistribute toward the poles where gravity is very slightly stronger, due to Earth being an oblate spheroid. The effect wouldn't be huge. We're talking about water levels dropping at the equator and rising at the poles by maybe 100 meters or so, but that would dramatically change coastlines. Equatorial regions would gain land as water drains away. Polar regions would be more flooded. More importantly, water would freeze on the night side and evaporate on the day side. Over time, you'd have a net migration of water from day to night, carried through the atmosphere as water vapor, then deposited as snow and ice on the night side. The question is whether this process eventually locks up all the water on the night side as ice, or whether circulation brings enough water back to maintain oceans on the day side and in the Terminator zone. Again, this depends on circulation patterns and timescales. If we're thinking about the immediate aftermath, the first centuries after Earth stops, there would definitely still be oceans on the day side and liquid water in the Terminator zone. Over longer periods, thousands or millions of years, water might gradually accumulate on the night side as massive ice sheets. But there's a counterbalance: precipitation. Water that evaporates on the day side doesn't instantly teleport to the night side. It forms clouds, gets carried by winds and falls as rain. Some of that rain falls in the Terminator zone, where it can remain liquid and flow back toward the day side as rivers. This circulation might be enough to maintain a water cycle, at least in the Terminator zone. So we'd probably end up with reduced ocean coverage on the day side, extensive ice deposits on the night side, and active water cycling in the Terminator zone. The Terminator would have rivers flowing both directions, toward the day side from rainfall and toward the night side from melting ice during seasonal shifts. Now let's address the magnetic field, because this is critical for long-term habitability. Earth's magnetic field protects us from the solar wind, the stream of charged particles constantly flowing from the sun. Without that protection, the solar wind would gradually strip away our atmosphere, just as it did to Mars after Mars lost its magnetic field billions of years ago. Earth's magnetic field is generated by the geodynamo, the churning of liquid iron in the outer core. This churning is driven by convection. Hot iron rises from near the solid inner core, cools and sinks back down. Earth's rotation organizes these convection currents, giving the magnetic field its overall structure. If Earth's rotation stopped, what happens to the geodynamo? There are two possibilities depending on what exactly stops rotating. Possibility 1, only the crust and mantle stop rotating, but the liquid outer core keeps spinning due to its own angular momentum. The core is mechanically decoupled from the surface. It's liquid, so it can rotate independently. If the core keeps spinning while the surface stops, the geodynamo would continue working, and the magnetic field would persist. Of course, the core wouldn't keep spinning forever. Friction at the boundary between the core and the mantle would gradually slow it down, but this process would take thousands or millions of years. For the timescales we're thinking about, generations of human survival, the magnetic field would remain intact. Possibility 2, the entire planet stops rotating, including the core. In this case, the geodynamo would be disrupted. Without rotation to organize the convection currents, the magnetic field would become chaotic and eventually collapse. This would be bad. Without the magnetic field, the solar wind would start stripping away the atmosphere. However, atmospheric loss is a slow process. Mars lost most of its atmosphere over hundreds of millions of years. Earth has a stronger gravity well, so it would hold onto its atmosphere longer, even without magnetic protection. We'd have time, probably millions of years, before atmospheric loss became a serious problem. But there would be immediate effects. Without the magnetosphere, more solar radiation would reach the surface. Increased exposure to cosmic rays and solar particles. Higher cancer rates, more mutation-causing radiation, potential damage to electronics and satellites. Life would be possible, but there would be new hazards to deal with. For our scenario, let's assume the optimistic case. The core keeps spinning. The magnetic field remains intact. This makes long-term survival more plausible, and avoids adding yet another catastrophic problem to an already difficult situation. There's one more physics question worth addressing: stability. If Earth somehow stopped rotating, would it stay stopped? Or would gravitational interactions with the Sun and Moon eventually start it spinning again? The answer is that it would stay stopped, more or less. Once angular momentum is removed from a system, it doesn't spontaneously come back. The Sun and Moon would create tidal forces that would try to change Earth's rotation, but these forces are very weak and would take billions of years to have significant effects. There is one interesting wrinkle: the Moon's orbit would be affected. Right now, the Moon is slowly moving away from Earth due to tidal interactions. The same friction that's slowing Earth's rotation is causing the Moon to gradually drift outward. If Earth's rotation stopped, this process would reverse. The Moon would start to slowly move inward, eventually getting close enough to be torn apart by Earth's gravity in what's called the Roche limit. But this would take tens of millions of years, so it's not an immediate concern. So the physics checks out mostly. A stopped Earth would be strange and hostile, but not immediately impossible. The atmosphere would remain, though redistributed. The oceans would remain, though frozen on one side. The magnetic field might remain, depending on the details. And life, as we've explored, could adapt to the new conditions. It wouldn't be easy. Survival would require adaptation on every level: biological, technological, cultural. But it wouldn't be impossible either. The physics allows for it. The question becomes whether life, particularly human life, has the resilience and creativity to make it work. And that brings us to the practical question: if Earth stopped spinning tomorrow and some of us somehow survived the initial catastrophe, could humanity actually make it work? Could we build a civilization on a stopped Earth? Could we not just survive but thrive? That's what we'll explore next. The practicalities of human survival, the engineering challenges, the resource constraints, the question of whether a technological civilization could maintain itself in the Terminator zone, and whether that life would be worth living. Let's be honest from the start. Surviving the initial stop would be nearly impossible. The atmosphere moving at 1,000 miles per hour, the tsunamis, the energy release equivalent to 1 million dinosaur-killing asteroids. Almost everyone would die in the first few hours or days. We're talking about an extinction-level event that makes every disaster in human history look like a minor inconvenience. But let's engage in some optimistic science fiction. Let's say that somehow, through incredible luck or advanced warning, or being in exactly the right place, a small population of humans survives the initial catastrophe. Maybe they were in deep underground bunkers. Maybe they were near the poles where the rotational speed is lower. Maybe they were in submarines deep beneath the ocean surface. However it happens, some humans survive. The question then becomes, can they build a sustainable civilization? Can they not just cling to survival in the immediate aftermath, but actually establish communities that could last for generations? Could humanity have a future on a stopped Earth? The answer depends heavily on where they end up and what resources they have access to. Let's consider the three main options: the Terminator zone, underground on the night side, and the habitable band on the day side. The Terminator zone is probably the most appealing option. You have light, which is psychologically important and useful for growing food. You have moderate temperatures, not comfortable, but survivable without extreme technological intervention. You have water from rainfall and rivers. You have constant wind that could be harnessed for power. And you have access to resources from both the day and night sides, if you're willing to venture into those more extreme zones. Building in the Terminator zone would require specific adaptations. Buildings would need to be low profile and aerodynamic to handle the constant wind. One side would face toward the dayside's heat, so you'd need excellent insulation and possibly cooling systems. The other side would face toward the night side's cold, requiring equally good insulation to keep heat in. It's like trying to build a structure that's simultaneously a desert house and an Arctic shelter. Food production would be challenging but possible. The light levels in the Terminator zone, that perpetual twilight, are low but sufficient for photosynthesis. You'd want to grow crops that are adapted to low light and cool temperatures. Leafy greens, root vegetables, certain grains. Greenhouses with supplemental LED lighting could dramatically increase yield, using electricity from wind turbines. Water wouldn't be a major problem. The Terminator zone would receive regular rainfall from water vapor condensing as it moves from the hot day side to the cool night side. Rivers would flow through the zone, and you could build cisterns to collect and store water during drier periods. Water purification would be necessary, but the technology for that is well established. Energy is where the Terminator zone really shines. Wind power would be abundant and reliable. Unlike current Earth, where wind is variable and unpredictable, the Terminator zone has steady, consistent winds flowing in one direction. You could line the zone with wind turbines and generate power continuously. Solar panels on the day-facing side could capture additional energy from that perpetual golden hour sunlight. And if you drill deep enough, geothermal energy is available everywhere on the planet. With abundant energy, you can solve a lot of problems. You can run greenhouses with artificial lighting. You can power water purification systems. You can maintain comfortable indoor temperatures despite the extreme conditions outside. You can run computers, communication systems, medical equipment. Energy is the foundation of technological civilization, and the Terminator zone could provide it. The main limitation in the Terminator zone would be population size. The zone is only a few hundred to maybe 1,000 kilometers wide, wrapped around the entire planet. That's a lot of land area in total, but it's stretched thin. And not all of it would be equally habitable. Some latitudes would be better than others. Some regions would have better water access or more stable temperatures. You might be able to support a population of a few million people, maybe tens of millions if you're very efficient, but not billions. The days of Earth supporting 8 billion humans would be over. Now let's consider underground survival on the night side. This would be a completely different way of life. No natural light, no weather, no sky, just artificial environments deep in the Earth, where geothermal heat keeps things warm enough for life. The technology for underground survival is essentially the same as what we'd need if the sun disappeared entirely, something we've explored in previous thought experiments. Hydroponic farming under LED grow lights, closed-loop life support systems that recycle air and water, geothermal power for energy, living spaces carved from rock or built in natural caverns. The advantage of the night side is stability. The surface is frozen and dead, but underground temperatures are constant. There's no weather to worry about, no storms, no seasonal variations. Once you build your infrastructure, it stays stable. The main challenges are psychological, living in artificial light in enclosed spaces, never seeing the sun or stars except as stories. Children born underground would grow up in a world utterly different from the Earth their ancestors knew. They'd never see a sunrise, never feel rain, never experience wind or clouds or the night sky. Their entire world would be corridors and chambers, gardens lit by LEDs, the constant hum of ventilation systems. It would be survivable, but would it be a life worth living? That's a philosophical question each person would have to answer for themselves. One advantage of underground colonies: They could be located almost anywhere on the night side. As long as you can drill deep enough to reach stable temperatures and access geothermal heat, you can build a settlement. This means the potential population could be larger than the Terminator zone. You have an entire hemisphere to work with, not just a narrow ring. The dayside habitable band would be the least appealing option, but still possible. This would be the zone far enough from the subsolar point that temperatures are merely very hot, rather than lethal. Maybe 120 to 140 degrees Fahrenheit survival would require serious heat management. Buildings would need to be heavily insulated, with reflective surfaces to minimize heat absorption. Underground components would be essential. The deeper you go, the cooler it gets. You'd probably spend most of your time underground and only venture to the surface during the cooler seasons, or in protective gear. Water would be a major challenge. At those temperatures, any standing water evaporates quickly. You'd need to capture water from the air as it condenses, or pipe it in from cooler regions, or access deep aquifers. Every drop would need to be carefully managed and recycled. Growing food would be nearly impossible on the surface. You'd need underground farms with cooling systems, or sealed greenhouses with temperature control. The energy requirements would be substantial. Solar power would be abundant. You have constant, intense sunlight, but you'd need a lot of it to run all the cooling and life support systems. Honestly, if you have the technology to survive in the dayside habitable band, you might as well go underground on the night side, where at least you don't have to fight the heat. The dayside would probably end up mostly uninhabited, except for resource extraction, mining operations, solar power arrays, automated systems that can handle the heat better than humans can. So the realistic options for human civilization are the Terminator zone and underground. Both are possible with current or near-future technology. Both could support populations large enough to maintain genetic diversity and cultural continuity. Both could potentially last for thousands of years if properly managed. But there would be limitations. The global population would be much smaller than today. Travel between settlements would be difficult. Crossing into the extreme zones of day or night requires preparation and protective gear. Communication would be easier, assuming you can maintain satellite networks or lay cables through the Terminator zone. But the idea of a unified global civilization would be gone. You'd have isolated communities, each adapted to their particular region. Trade would be important. The Terminator zone might have excess food production, but need minerals from the day side. Underground communities on the night side might have access to certain ores or frozen gases, but need manufactured goods from the Terminator. Resource distribution would be uneven, creating both opportunities and potential conflicts. Culture would evolve in strange directions. Terminator zone people might develop a culture centered around wind and twilight, with myths about the lost days when the sun moved across the sky. Underground dwellers might have a culture focused on depth and darkness, with the surface world becoming almost mythical in their stories. Dayside workers, if any remain, might see themselves as hardy explorers, braving the inferno to bring back resources for the sheltered people in cooler zones. Let's compare this scenario to others we've explored. If the sun disappeared entirely, we'd all have to go underground. There's no alternative. If we had two suns, Earth would be too hot across most of the surface, forcing us into polar regions or underground. A stopped Earth is actually more forgiving than either of those scenarios. At least here we have the Terminator zone, a genuine surface environment where humans could live with manageable technology. On the other hand, the initial catastrophe of Earth stopping would be worse than either of those scenarios. The sun disappearing would be gradual. We'd have time to prepare, to build infrastructure, to move people to safety. Two suns would heat things up over time, not instantly. But Earth stopping, that's an immediate, catastrophic event that kills almost everyone before they have a chance to react. So the ranking would be something like initial survival, nearly impossible, long-term survival after the initial catastrophe, actually quite feasible, especially in the Terminator zone. Overall, compared to current Earth, dramatically worse but not completely hopeless. One thing that might help, advance warning. If we somehow knew Earth's rotation was going to stop, say we detected it slowing down over a period of years, we could build bunkers near the poles where the rotational speed is lowest, stockpile supplies, design settlements for the Terminator zone, move populations away from coasts and low-lying areas that would be hit by tsunamis. With preparation, the survival rate would be much higher. But even with preparation, we'd be looking at a massive reduction in population and quality of life. Billions would die. The survivors would live in constrained environments, using technology to compensate for a planet that's no longer naturally hospitable. It would be survival, but it would be hard. There's something sobering about this thought experiment. It makes you realize how much we depend on things we never think about. Earth's rotation seems like just a fact, something that's always been true and always will be. We don't feel it, don't see it, barely acknowledge it, except when we talk about time zones or sunrise times. But it's not just a fact. It's the foundation of almost everything that makes Earth habitable. The day-night cycle, the spreading of heat around the planet, the Coriolis effect that organizes our weather, the magnetic field that protects our atmosphere. Take away rotation and you take away the very conditions that allow life to thrive. Could humanity survive on a stopped Earth? Yes, probably. At least in reduced numbers and with significant technological support. Would we want to? That's a different question. Life on a stopped Earth would be a constant struggle against environmental extremes. We'd survive, but we'd be diminished, constrained, always aware that we're living in a broken world that requires constant maintenance to remain habitable. And yet, there's something inspiring about the idea that even in such catastrophic circumstances, humanity could persist. We're clever, we're adaptable, we're stubborn. Give us a problem, and we'll find a solution, even if that solution involves living in perpetual twilight or in caves deep underground. We've survived ice ages and volcanic winters. We've crossed oceans and deserts and Arctic wastes. We've proven that we can live in almost any environment Earth offers. A stopped Earth would be the ultimate test of that adaptability, and while most of us wouldn't survive the initial event, those who did would have the chance to prove what humanity can do when backed into a corner, build a civilization on the edge between light and dark. Create new cultures adapted to impossible conditions. Show that life, even human life, is more resilient than we imagine. So yes, humanity could survive on a stopped Earth. Not easily, not pleasantly, and certainly not in the numbers we have now. But we could do it. We could make it work. That's both reassuring and humbling. Reassuring because it shows our resilience. Humbling because it reminds us how much we depend on conditions we take for granted. But there's a deeper lesson here, beyond the question of survival. Let's explore what this thought experiment teaches us about our actual world, the one that's still spinning beneath us right now. So, we've imagined Earth without its spin. We've explored the eternal day, the frozen night, the twilight zone between them. We've thought about how life would adapt and whether humanity could survive. But what's the point of all this? Why spend time imagining something that can't happen? The answer is that impossible scenarios help us appreciate what's real. By imagining Earth stopped, we gain perspective on Earth spinning. by exploring what we'd lose, we understand what we have. Thought experiments aren't about the scenario itself. They're about the insights we gain from the contrast. Let's start with the most obvious lesson. We're spinning right now, and it's giving us everything. 1,000 miles per hour at the equator. Fast enough that if you could somehow stand still while Earth rotated beneath you, you'd see the entire planet pass by in just 24 hours, and yet you can't feel it. The motion that makes life possible is completely invisible to us. That spin creates the day-night cycle that every living thing depends on. Plants open their leaves in the morning and close them at night. Animals wake and sleep according to the sun's position. Humans structure their entire lives around the cycle. Work during the day, rest at night, plan their schedules around sunrise and sunset. The 24-hour day is so fundamental to how we organize our existence that we barely think about it. But it's not inevitable. It's a consequence of rotation. Take away the spin and you lose the cycle. You end up with eternal day or eternal night, both of which are hostile to life as we know it. The comfortable rhythm of light and darkness that we take for granted only exists because Earth keeps spinning. Then there's temperature distribution. Right now, Earth's rotation spreads heat around the planet. Every location gets a turn facing the sun, warming up, then turns away to cool down. This prevents any one spot from getting too hot or too cold. The equator would be much hotter if it faced the sun continuously. The poles would be much colder if they never faced the sun at all. More than that, rotation drives atmospheric circulation through the Coriolis effect. Air flowing from the equator toward the poles gets deflected by Earth's rotation, creating the trade winds, the westerlies, the jet streams. These wind patterns drive weather systems, distribute moisture, and generally make Earth's climate much more moderate and predictable than it would be otherwise. Without rotation, you'd still have winds driven by temperature differences, but they'd be simpler and more extreme. Just straight-line flow from hot to cold with no organization, no spiral patterns, no complexity. Weather would be less interesting and probably more violent. The elegant patterns we see in satellite images of hurricanes and fronts, those only exist because Earth spins. Ocean currents work the same way. The Gulf Stream carries warm water from the tropics toward Europe, moderating the climate there. The currents in the Pacific and Indian Oceans distribute heat and nutrients. These currents are driven partly by temperature and salinity differences, but they're organized by the Coriolis effect. Without Earth's rotation, ocean circulation would be completely different, and many regions that are currently habitable would have much harsher climates. And then there's the magnetic field. We don't think about it much because we can't see it or feel it, but it's crucial. The magnetosphere extends far out into space, deflecting the solar wind, that constant stream of charged particles from the sun that would otherwise strip away our atmosphere. Mars lost its magnetic field billions of years ago, and gradually lost most of its atmosphere as a result. Earth's rotation helps maintain the geodynamo that creates our magnetic field, keeping our atmosphere intact. Even the shape of our planet is a gift of rotation. That equatorial bulge, the fact that Earth is wider at the equator than from pole to pole, exists because of centrifugal force from spinning. It's a small effect, less than 1%, but it's measurable. Our planet's shape itself bears the mark of its motion. So rotation gives us the day-night cycle, moderate temperatures, organized weather patterns, stable ocean currents, protection from solar wind, and even affects the shape of the planet. That's a lot to get from something we can't feel. It's like discovering that your house has been built on a foundation you never knew existed, and that foundation is holding up everything. There's a broader lesson here about invisible support systems. We tend to notice things that are active, changing, demanding our attention. We don't notice things that are constant. The air we breathe, the gravity that keeps us grounded, the magnetic field that protects us, the rotation that structures our days, these are all invisible to us because they never change, or rather, they change so slowly that we never notice. It's only when we imagine these things being different that we realize how much we depend on them. Imagine Earth without an atmosphere. Suddenly you appreciate air. Imagine Earth without gravity. Suddenly you appreciate having your feet on the ground. Imagine Earth without rotation. Suddenly you appreciate the sunrise. This extends beyond planetary physics to everything in life. We don't think about infrastructure until the power goes out or the water stops running. We don't appreciate our health until we get sick. We don't value relationships until they're threatened. The things that support us, that make our lives possible, tend to be invisible until they're gone. Maybe that's the real value of thought experiments like this. They make the invisible visible. They force us to imagine life without something we normally take for granted, and in doing so, they help us appreciate what we actually have. Let's talk about cycles, because the day-night cycle is just one example of the rhythms that structure life on Earth. We have daily cycles, sunrise and sunset monthly cycles, the phases of the moon. Yearly cycles, the seasons. These rhythms give structure to time, create patterns we can rely on, provide reference points for organizing our lives. On a stopped Earth, most of these cycles would disappear. No daily cycle because there's no rotation. The seasons would still exist due to Earth's orbital motion and axial tilt, but they'd be different. Not a change in day length, but a shift in where the sun appears relative to your position on the planet. The moon would still orbit, but without day-night cycles, its phases would be less meaningful. Living without these cycles would be disorienting in ways that go beyond the physical challenges. Humans are pattern-seeking creatures. We find comfort in repetition, in knowing what comes next. The sun rises, the sun sets, the pattern repeats. It's predictable, reliable. Remove that pattern, and you remove a source of psychological stability. You'd need to create artificial cycles to replace the natural ones. Set your lights to turn on and off on a schedule. Organize your community's activities around clock time rather than sun time. Impose structure where nature no longer provides it. It would work, but it would be effortful in a way that current Earth never requires. Here, the cycles just happen, and we flow with them. There's something profound about this. Natural cycles are free. They require no energy, no maintenance, no conscious effort. The sun rises whether we want it to or not, whether we're paying attention or not. It's been rising every day for billions of years, and will continue for billions more. That reliability is a gift we rarely acknowledge. Another lesson, change versus permanence. Right now, it feels like Earth has always been spinning, and always will be. The day-night cycle is so constant, so reliable, that it seems eternal, but it's not. Earth is actually slowing down, very gradually, but measurably. Days are getting longer by about 1.7 milliseconds per century, due to tidal friction from the moon. That doesn't sound like much, and on human timescales it isn't. You will never notice a day getting longer. Your children won't notice. Your great-great-great-grandchildren won't notice. But over geological time, it adds up. 400 million years ago, a day was about 22 hours. 4 billion years ago, a day was only 6 hours. And this process will continue. In 600 million years, a day will be 25 hours long. Eventually, billions of years from now, Earth might become tidally locked to the moon, with one side permanently facing it. Earth's rotation, which seems eternal, is actually temporary. Everything changes given enough time. This is both humbling and oddly comforting. Humbling because it reminds us that nothing is permanent, not even the fundamental features of our planet. Comforting because it reminds us that change happens on timescales so vast that we need never worry about them. Yes, Earth is slowing down, but not in any way that affects our lives or our children's lives or our civilization's foreseeable future. It's a perspective thing. On human timescales, Earth's rotation is permanent and unchanging. On geological timescales, it's slowly evolving. Both perspectives are true. The trick is knowing which perspective is appropriate for what you're thinking about. Let's think about adaptation. We've explored how life would adapt to a stopped Earth. Plants changing their pigments, animals losing their eyes, humans building underground cities. The message there is that life is remarkably resilient. Given even harsh conditions, evolution finds solutions. Life doesn't give up easily. But there's a corollary to that. We're already adapted to spinning. Every organism on Earth has been shaped by rotation. Our circadian rhythms, our sleep patterns, our agricultural cycles, our cultural practices around sunrise and sunset, all of these are adaptations to a spinning planet. We're not adapted to Earth in general. We're adapted to this specific version of Earth, the one that rotates. Change the fundamental conditions, and all those adaptations become liabilities. Suddenly, our circadian rhythms are useless, because there's no day-night cycle to synchronize with. Our agricultural knowledge is based on seasons that no longer work the same way. Our cities are built in locations that made sense on a spinning Earth, but might be uninhabitable on a stopped one. This is true for any fundamental change. We're adapted to our environment, whatever that environment happens to be. Change the environment dramatically, and we'd need to adapt or perish. It's a reminder that we're not separate from Earth, above it or independent of it. We're part of it, shaped by it, dependent on its specific conditions. And maybe that's the most important lesson from this entire thought experiment. Earth's rotation isn't just a fun fact about astronomy, it's the foundation of the world we live in. The motion we never feel creates the conditions we completely depend on. Remove that motion, and you remove the basis for almost everything that makes Earth habitable. We are, in a very real sense, children of rotation, born on a spinning world, adapted to its rhythms, shaped by its cycles. The day-night pattern isn't just something that happens around us, it's something that happens through us. Woven into our biology and culture so deeply we barely recognize it. So when we imagine Earth stopped, we're not just imagining a different planet. We're imagining a world where almost nothing that we rely on still works, where the most fundamental assumptions about how life operates, that the sun rises, that time is organized into days, that heat gets distributed around the planet, all become false. It's a stark reminder of how much we depend on things we don't control and didn't create. Earth's rotation predates humanity by billions of years. It will continue long after we're gone. We didn't make it happen, we can't stop it, we can barely measure its gradual slowdown. It's a force completely beyond our influence, and yet it shapes every aspect of our existence. That's simultaneously humbling and awe-inspiring. Humbling because it reminds us how dependent we are, how fragile our existence is relative to the massive forces that sustain it. Awe-inspiring because it reveals the incredible elegance of the system we're part of. A system where something as simple as rotation creates complexity enough for life, for consciousness, for civilizations to emerge. Maybe the real lesson is gratitude, not the superficial kind where you say you're grateful but don't really feel it. The deep kind where you truly understand how remarkable it is that the conditions for your existence happen to be met, that Earth spins at exactly the right speed to create day and night without extreme temperature swings, that this spin has been stable for billions of years, that you happen to live in the brief window of cosmic time when Earth is spinning at a rate that makes complex life possible. Tomorrow the sun will rise, not because of anything you did, but because Earth continues its billion-year-old spin. The day will follow the night, as it always has. And in that simple, reliable pattern lies the foundation for everything you experience. Every meal, every conversation, every moment of your life exists because Earth keeps spinning. We explored stillness to appreciate motion. We imagined eternal day and night to cherish the cycle of both. We contemplated a broken world to understand how complete our actual world is. And now we return to reality, to a planet that spins, to days that pass, to rhythms that continue. Earth is still spinning beneath you, still carrying you through space at 1,000 miles per hour, still creating the conditions that make your life possible, still turning toward the sun and away from it, day after day, year after year, with a reliability that defies comprehension. And you still can't feel it, but now maybe you appreciate it. Here's something remarkable. The scenario we've been imagining isn't purely hypothetical. Out there in the universe right now, there are planets experiencing exactly what we've described worlds, with one face permanently toward their star and one face forever in darkness. Planets with Terminator zones where life might exist. Real places, orbiting real stars, where the conditions we've imagined are actual reality. They're called tidally locked planets, and they're remarkably common. In fact, they might be the most common type of potentially habitable planet in the universe, which means that if life exists elsewhere, it might very well be living in the conditions we've been exploring. Eternal twilight, constant winds, a narrow, habitable zone between extremes. Let's start close to home, relatively speaking. The closest star to our Sun is Proxima Centauri, a red dwarf about 4.2 light-years away. It has at least 2 planets, and one of them, Proxima Centauri b, sits right in the middle of the habitable zone, the region where liquid water could exist on a planet's surface. Proxima Centauri b is probably tidally locked. It orbits very close to its star, much closer than Mercury orbits our Sun, completing one orbit every 11.2 Earth days. At that distance, tidal forces from the star would have long ago slowed the planet's rotation until one face permanently faces Proxima Centauri. So right now, just over 4 light-years away, there's a planet where one hemisphere is bathed in perpetual red light from its star, and the other hemisphere sits in endless darkness. Between them is a ring of twilight, and that might be where life exists, if it exists at all. We don't know if Proxima Centauri b has an atmosphere. We don't know if it has water. We certainly don't know if it has life. But the conditions are potentially right. The temperature could be moderate in the Terminator zone. Water could be liquid. And if our thought experiment has taught us anything, it's that life might find a way even in such seemingly alien conditions. The star itself is quite different from our Sun. Proxima Centauri is a red dwarf, much smaller, much cooler, much dimmer. It puts out mostly red and infrared light, rather than the full spectrum we're used to. Any photosynthetic life on Proxima Centauri b would need to adapt to that red shifted light, probably using different pigments than Earth's green chlorophyll. Red dwarfs are also unstable when they're young, prone to powerful flares that could strip away a planet's atmosphere. But Proxima Centauri is old, about 4.85 billion years, roughly the same age as our Sun its flaring has calmed down. If Proxima Centauri b has an atmosphere, it's probably survived the violent early period and might be stable now. This is the closest exoplanet we know of that could potentially harbour life. Our nearest neighbour in the cosmos might be a tidally locked world with life clinging to its Terminator zone. That's simultaneously exciting and sobering. Exciting because it means potentially habitable worlds are common. Sobering because it suggests the universe might be full of planets less hospitable than Earth. But Proxima Centauri b is just one example. Let's talk about the TRAPPIST-1 system, which is perhaps the most fascinating planetary system we've discovered so far. It's about 40 light-years away, not close, but close enough that we can study it in detail. TRAPPIST-1 is another red dwarf, even smaller and cooler than Proxima Centauri. And orbiting it are 7 Earth-sized planets, all packed into a space smaller than the orbit of Mercury 3. Of these planets sit in the habitable zone, and most or all of them are probably tidally locked. Think about that for a moment. 7 Earth-sized worlds, most of them potentially experiencing the conditions we've been imagining. 7 planets with eternal day sides and eternal night sides. 7 Terminator zones where conditions might be just right for life. It's like having 7 natural experiments running simultaneously, each testing whether life can emerge on a tidally locked world. The TRAPPIST-1 planets orbit so close to their star that from the surface of one planet, the other planets would be visible in the sky as distinct disks, not just points of light. You could see continents on the neighbouring worlds, watch weather systems move across their surfaces. It would be a spectacular sky. Multiple planets visible at once, some larger than our moon appears from Earth. If any of these planets have atmospheres, and some observations suggest they might, those atmospheres would be constantly bombarded by radiation from the star and from the other planets. The whole system would be interconnected in ways we don't fully understand yet. Material ejected from one planet might reach another. Life arising on one planet might theoretically spread to another through impacts. The planets also have interesting names: TRAPPIST-1b through TRAPPIST-1h, with TRAPPIST-1d, E and F being the ones in the habitable zone. They're named after the telescope that discovered them, TRAPPIST, the Transiting Planets and Planetesimals Small Telescope. It's a fitting name for a discovery that trapped the attention of the entire astronomical community. Scientists are particularly excited about TRAPPIST-1e, which seems to have the best combination of size, temperature, and orbital position for potential habitability. If we had to pick one planet in that system to search for life, that would be it. And if TRAPPIST-1e does have life, that life would almost certainly be adapted to tidally locked conditions. Now, it's important to understand why tidally locked planets are so common around red dwarfs. Red dwarfs are much dimmer than our Sun, which means their habitable zones are much closer to the star. And tidal forces, the forces that cause tidal locking, get stronger with proximity. So any planet close enough to a red dwarf to be in the habitable zone is also close enough to become tidally locked relatively quickly. This is significant because red dwarfs make up about 70 to 75% of all stars in our galaxy. They're by far the most common type of star, which means that most potentially habitable planets in the Milky Way are probably tidally locked. The scenario we've been imagining, eternal day, eternal night, life in the Terminator zone, might be the norm, not the exception. Earth, with its day-night cycle and moderate rotation, might actually be unusual. We might be the weird ones living on a planet with the luxury of regular sunrises and sunsets. If you picked a random habitable planet from the galaxy, you'd be more likely to land in a Terminator zone than in a place with Earth-like conditions. That changes how we think about the search for life. For decades, we've been looking for planets like Earth. Similar size, similar distance from a sun-like star, similar conditions. But maybe we should be looking at tidally locked worlds around red dwarfs. Maybe the most common form of life in the universe is adapted to conditions we've only recently started to consider. And scientists are taking this seriously. Recent models suggest that tidally locked planets might actually be more stable and habitable than we initially thought. The key is the atmosphere. If a planet has a thick enough atmosphere, wind circulation could distribute heat from the day side to the night side, preventing the temperature extremes we've been describing. You'd still have a temperature gradient, but it might be moderate enough that life could exist across a wider area, not just in the Terminator zone. Some models even suggest that tidally locked planets might have oceans that cover most of the day side, with the water acting as a heat sink and moderating the temperature. The subsolar point would have constant evaporation, but the ocean would distribute heat and prevent any one area from getting too hot. The night side would still freeze, but the day side might be surprisingly livable. These are just models, of course. We won't know what conditions are really like on tidally locked planets until we can study them more directly, but the fact that scientists are seriously considering these worlds as potentially habitable is remarkable. A decade ago, most people would have assumed tidally locked planets were too extreme for life. Now, we're not so sure. There are other interesting examples too. LHS 1140b is a planet about 49 light-years away, orbiting a red dwarf. It's bigger than Earth, a super-Earth, and it might have conditions suitable for life in its Terminator zone. Kepler 442b is another candidate, a super-Earth in the habitable zone of its star, possibly tidally locked. The list keeps growing as we discover more exoplanets. Each of these worlds is a natural experiment. Each one is testing whether life can arise and survive under tidally locked conditions. We're not going to visit them anytime soon. They're dozens of light-years away, and our fastest spacecraft would take tens of thousands of years to reach even the closest ones. But we can study them from here, analysing the atmospheres with telescopes, looking for signs of water, oxygen, methane, the chemical signatures that might indicate life. The James Webb Space Telescope, launched in 2021, is capable of analysing the atmospheres of some of these planets. It can look at the light passing through a planet's atmosphere as the planet transits in front of its star, and from the absorption lines in that light determine what gases are present. If we find oxygen and methane together, a combination that's hard to explain without life, that would be compelling evidence. We might, within the next few decades, discover life on a tidally locked planet. We might find evidence of photosynthesis happening in perpetual dim light, or ecosystems adapted to constant wind, or civilizations that have never seen their sun move across the sky. And if we do, everything we've imagined in this thought experiment would suddenly become much more concrete. It would also tell us something profound about life itself. If life can thrive on tidally locked worlds, and thrive not just survive, but build complex ecosystems, evolve intelligence, maybe even develop technology, then life is more versatile than we thought. It means the universe might be teeming with living things, just not in places or conditions we initially expected. There's something humbling about that. We've spent this entire discussion imagining how difficult life would be on a stopped Earth, how humanity would struggle to survive in the Terminator zone or underground. But that difficult scenario might be normal for life elsewhere. Organisms on other worlds might look at Earth and think how strange it must be to have the sun move across the sky every day, to have temperatures that change with such regularity, to have a planet that spins so fast. From their perspective, we might be the ones living in unusual conditions. They might wonder how we handle the constant change, the day-night cycle, the way temperatures drop every 12 hours, they might find it as alien as we find their eternal twilight. And maybe that's the most important lesson from these real examples. What seems impossible or extreme to us might be normal somewhere else. What we consider essential, like day and night, might be optional. What we think of as the conditions for life might just be the conditions for life like us, on planets like ours, orbiting stars like our sun. The universe is vast, and it contains multitudes, tidally locked planets, binary star systems, super-Earths, mini-Neptunes, planets orbiting pulsars, rogue planets drifting through interstellar space. Each type of world offers different conditions, different challenges, different possibilities for life. And somewhere out there, 40 or 50 light-years away, there might be a planet with a Terminator zone where organisms are adapted to perpetual twilight, where plants have evolved to capture dim red light, where animals navigate by the constant wind, where intelligent beings look up at a sun that never moves and wonder if there are other worlds where things are different. Maybe they're telling each other stories about impossible planets where the sun moves across the sky, where day and night cycle endlessly, where the wind changes direction and the temperature varies hour by hour. Maybe they're imagining what life would be like on a spinning world. And maybe, just maybe, they're wondering if anyone out there is thinking about them. Imagine you're born on a stopped Earth, generations after the initial catastrophe. You grow up in the Terminator zone, in a settlement where the sun sits perpetually on the horizon, casting long shadows that never move. You've never experienced a sunrise or a sunset in the way your ancestors described them. To you, the sun is simply there, constant, unchanging, like a lamp that's always on. How would you think about time? On current Earth, we use the sun's position to organize our days. Morning, noon, evening, night. These concepts are tied to where the sun is in the sky, but in the Terminator zone, the sun never moves. It's always the same time of day, visually speaking. Always that golden hour light, always those long shadows. You'd need to create artificial structure. Maybe your community uses clocks divided into work periods and rest periods, completely divorced from natural light. Maybe you organize time around other patterns, meal times, community gatherings, the slow shift of stars over the course of a year. But the old way of telling time, the way humans have done it for millennia by watching the sun, wouldn't work anymore. There's something profound about that. Time wouldn't be a natural phenomenon you observe. It would be a social construct you maintain. You'd sleep when the community agrees it's time to sleep. Work when it's time to work. Not because the light tells you to, but because you've all agreed on a schedule. Time becomes a choice, not a given. And what about the stories you'd tell? Every culture on Earth has mythology about the sun. Solar deities, creation myths involving the sun's movement, legends about why day follows night. Ancient Egyptians had Ra sailing his boat across the sky. Greeks had Helios driving his chariot. Norse mythology had Sol pursued by a wolf. These stories make sense on a spinning Earth where the sun appears to move. But on a stopped Earth, what myths would emerge? The sun doesn't move, so you can't create stories about its journey. Instead, the sun becomes a permanent presence, an eternal witness, perhaps a god that never sleeps, never leaves, never stops watching. That would create a very different relationship with the divine. In the Terminator zone, you might develop myths about balance, the sun on one side, darkness on the other, and your people living in between, neither in light nor in shadow, but in the place where both meet. You might create stories about the eternal struggle between day and night, with the Terminator zone as the battlefield or the border or the sacred space where opposing forces achieve equilibrium. On the night side, the sun becomes a lost god. Your ancestors remember it. Stories passed down about a time when there was warmth and light from above, but you've never seen it. You live in darkness, sustained by the earth's warmth from below. The sun becomes mythological in a different sense, not a god you worship, but one you've lost, one your people are separated from. Your myths might be about exile, about waiting for the return of light that never comes. And the day side? If anyone lives there in the habitable band or in protected settlements, they experience the opposite. Eternal light, unrelenting heat, a sun that never grants them the mercy of darkness. Their myths might be about endurance, about surviving under the constant gaze of an unforgiving sun, or about finding shelter, about the virtue of the shadow, about the few places where you can escape the light. Each region would develop its own mythology, its own way of making sense of conditions that would seem strange to us, but are normal to them, and all of these myths would include references to the lost world, the time before Earth stopped spinning, when the sun moved across the sky and day followed night in endless cycles. That old world would become legend, a paradise lost, a time of balance and plenty that can never return. Imagine the stories parents tell their children, not fairy tales about magic and adventure, or at least not just those, but stories about the spinning earth, about how your great-great-great-grandparents lived in a world where the sun rose in the morning and set in the evening, where you could tell time by shadows that moved across the ground, where the temperature dropped every night and rose every day in predictable patterns. Children would find these stories hard to believe. A moving sun, shadows that change. It would sound like fantasy, like impossible magic. They might not believe their ancestors really lived that way, and even if they do believe it, they can't truly understand it. You can't miss what you've never experienced. Art would be fascinating on a stopped Earth. In the Terminator zone, you'd have artists working with that perpetual golden hour light. The same light photographers on current Earth wait all day to capture. Every painting would be bathed in those warm tones. Every sculpture would cast those long, dramatic shadows. It would become the aesthetic norm, the only light anyone has ever painted by. But there would also be a longing, perhaps, art about the lost cycles, paintings imagining what a sunrise might look like, not painted from observation, but reconstructed from old descriptions and photographs that survived from before the stop artists trying to capture something they've never seen, working from imagination and inherited memory. You might see art movements based on depicting what's missing, paintings of darkness at noon, sculptures that create moving shadows through mechanical means, capturing the motion that the sun no longer provides, performance art, where people act out the daily cycle, one person holding a light and slowly moving it across a space while others pretend to live through a day. It would be both a celebration and a mourning, beauty created from loss. Music would be different too. On current Earth, many cultures have songs associated with different times of day. Morning songs, evening songs, lullabies for nighttime. But on a stopped Earth, those categories don't exist. What's a morning song when there's no morning? What's a lullaby when darkness never comes? You might develop music organized around other patterns. Songs for the work shift, songs for the rest shift, songs marking the slow seasonal changes as the Terminator zone shifts with Earth's orbit. Or maybe music becomes atemporal, not tied to any particular time because all times are essentially the same. You make music when you feel like it, when the community gathers, when someone has something to express. The constant wind in the Terminator zone would influence everything. Architecture, certainly, we've talked about that, but also music. Wind instruments would sound constantly if left outside. You might develop a culture where the wind itself is considered musical, where buildings are designed with openings that create harmonics when the wind blows, natural wind chimes on every structure, turning the whole settlement into an instrument that the wind plays. Philosophy would take interesting turns. On current Earth, much philosophy deals with change, with the nature of time, with cycles of growth and decay. These ideas make sense on a world where everything changes, where seasons turn and days pass. But on a stopped Earth, where conditions are essentially static, where the same light falls on the same land forever, you might develop philosophies centered on permanence. What does it mean to live in a world without natural renewal? On current Earth, we can always count on tomorrow being a new day, literally a fresh rotation, a new rising of the sun. Bad days end, seasons change, nothing stays the same forever. But in the Terminator zone, tomorrow looks exactly like today. The same light, the same wind, the same view. How do you find meaning in that constancy? You might develop philosophies about finding change within stillness, about internal growth when external conditions don't change, about creating your own cycles and rhythms when the world provides none. It would be a philosophy of intentionality, making meaning rather than finding it, creating structure rather than observing it. Or you might go the other way and embrace the stillness. Find peace in the unchanging nature of the world. No surprises, no unexpected changes, just the reliable constancy of the sun on the horizon and the wind from the same direction. For some people that might be comforting. The world is what it is, and it will remain what it is. There's a certain serenity in that. Language would evolve too. Words and concepts tied to rotation would gradually lose their meaning or change their definitions. Sunrise, sunset, afternoon, midnight. These words refer to positions of the sun that don't exist on a stopped Earth. They might persist as historical terms, referring to concepts from the old world that children learn about in school but never experience. Or new words would emerge, terms for the slight variations in light as the seasons shift the Terminator, words for different qualities of the perpetual twilight, names for the psychological states specific to life without circadian rhythms, a whole vocabulary developing around conditions that current humans never experience and thus have no need to name. The relationship between different regions would be fascinating. Imagine trade delegations from the Terminator zone visiting underground settlements on the night side. The Terminator dwellers would find the artificial light strange, the enclosed spaces claustrophobic. The underground dwellers would find the open sky overwhelming, the constant wind unsettling. Neither could survive long in the other's environment without protection. They'd be like different species almost, adapted to completely different worlds even though they're all human, all living on the same planet. Their cultures would be wildly different, their values, their art, their entire way of life shaped by their environment. They'd need translators not just for language, but for concepts, explaining to someone who's never seen the sun why perpetual twilight is beautiful, or explaining to someone who's never seen darkness why living underground isn't depressing. And there would be cultural exchange, inevitably. Music from the Terminator zone making its way to underground settlements. Stories from the night side being told to children in the twilight. Technologies developed in one region being adapted for use in another. Despite the physical separation, despite the vastly different living conditions, humans would find ways to connect, because that's what humans do. We tell stories, we make art, we create meaning, even where the universe doesn't provide it. We find patterns, build communities, develop cultures. We adapt not just biologically, but culturally, using stories and songs and myths to make sense of whatever world we find ourselves in. On a stopped Earth, humans would continue doing what we've always done, creating narrative, finding beauty, making the strange familiar through art and story and shared experience. The conditions would be alien, but the human response would be timeless. We'd take this broken world and make it ours, give it meaning, fill it with culture. And maybe, somewhere in the Terminator zone, there would be people who look at the sun on the horizon and find it beautiful. Not despite its stillness, but because of it, they'd appreciate the constancy, the reliability, the way the light never changes. They'd build their lives around that eternal golden hour and consider it normal, natural, the way things should be. They might even pity their ancestors who lived on a spinning Earth. All that chaos, they'd think, the sun moving constantly, never giving you a moment of visual stability, shadows changing, light levels shifting, the whole world in constant motion. How did anyone find peace in that? How strange it must have been to live in a world that never stood still. And they'd be right, in a way. Normal is whatever you're adapted to. Home is wherever you make it. Beauty exists in any world, even a stopped one, because beauty is something we create, not something we find. The universe is indifferent. It's humans who care, who see meaning, who tell stories about stillness and motion, light and dark, the world that was and the world that is. So even on a stopped Earth there would be stories. Different stories than ours, shaped by different conditions, but stories nonetheless. Because as long as there are humans, there will be narratives. We're a storytelling species. It's one of the things that makes us who we are. Take away our spinning world and we'll just tell new stories about the world that remains. So here we are, back where we started. Earth is still spinning beneath you. Right now, this moment, you're moving at roughly 1,000 miles per hour. The same speed you were moving when we began this journey together. The same speed you'll be moving when you drift off to sleep tonight. We've spent all this time imagining what would happen if that motion stopped. We've explored eternal day and frozen night. We've walked through the Terminator zone where the sun never moves. We've thought about how life would adapt, how humans might survive, what we'd lose and what we'd keep. But it was all imagination, a thought experiment, a way to appreciate what we actually have by contemplating its absence. And what we have is this, a planet that spins at exactly the right speed to create day and night, without extreme temperature swings. A rotation that's been stable for billions of years, that will continue for billions more, a motion so constant, so reliable, that we never think about it, until we imagine it stopping. Tomorrow morning, the sun will rise, not because the sun is moving, but because Earth is rotating toward it. You'll turn toward the light, carried by a planet that's been spinning since before there was life, before there were oceans, before there was anything alive to notice. And tomorrow night, the sun will set. Not because it's going anywhere, but because you're turning away from it, rotating into the shadow that Earth itself cast into space. And in that shadow, you'll rest, you'll sleep, you'll dream maybe of stillness or motion or whatever your mind conjures in the darkness. And then morning will come again, because Earth keeps spinning, because it always has, because the motion that makes everything possible continues, invisible and constant, whether you're paying attention or not. If you've enjoyed this exploration of a stopped Earth, if these ideas have given you something to think about as you drift off to sleep, consider subscribing to the Sleepy Astronomer. We explore the universe's biggest questions in a gentle, contemplative way, perfect for those nights when your mind is too active for sleep but too tired for anything intense. Next time, we might explore other impossible scenarios, other ways to break the universe, just to see what we'd learn from the breaking, other thought experiments that teach us to appreciate what we take for granted. But for now, it's enough to know this. You live on a spinning world, a world where day follows night and night follows day in an endless, reliable cycle. A world where the motion you can't feel creates the conditions you completely depend on. 1,000 miles per hour. That's how fast you're moving right now, and you can't feel a thing. But maybe now, after all this, you can appreciate it. Sleep well on your spinning planet. Rest easy knowing that tomorrow the sun will rise again, that the day-night cycle will continue, that Earth will keep rotating, as it always has, as it always will, at least for as long as any of us will be here to notice. Dream of stillness if you like. Imagine eternal twilight, or frozen darkness, or the strange beauty of a world that doesn't turn. But when you wake, you'll find yourself back on this spinning Earth, where sunrise still happens, where shadows still move, where the oldest rhythm in the solar system continues its dance. And there's something deeply comforting in that, something peaceful, knowing that beneath all the complexity of life, beneath all our worries and plans and daily concerns, there's this, Earth spinning, the sun rising, day following night following day. It's been going on for 4.5 billion years. It'll keep going for billions more. And tonight, like every night before it, and every night to come, you get to rest in that rhythm. You get to let the spin carry you into darkness and out again into light. Good night from the Sleepy Astronomer. Thank you for spinning with me through this thought experiment. May your dreams be peaceful, your rest be deep, and your appreciation for our rotating world be just a little bit stronger than it was before. Sweet dreams, wherever you are on this beautiful, spinning planet. The universe is vast and strange and full of wonders, and you're experiencing one of them right now.